Hey guys, welcome to another episode of the Human AI podcast. Today we're going to talk about metabolism. When we're fed, when we're starving. What about carb metabolism? How the organs interact during this process. We're talking a bit about diabetes and metabolism. And we're also going to talk about renal failure. So, I'm here with Grok, who's going to be explaining these things to us. Please cross-reference everything you hear. AI might be wrong sometimes, take it with a pinch of salt. However, hopefully you can find this entertaining and informative. Okay, Grok, let's shoot. Let's talk about metabolism in the fed and starved states first, shall we?
All right, let's dive into metabolism for the Human AI podcast. In the fed state, after you eat, your body's priority is to digest and store energy. Carbs break down into glucose, spiking blood sugar. Insulin kicks in, shuttling glucose into cells for energy or storing it as glycogen in the liver and muscles. Fats get stored as triglycerides, and amino acids from proteins go to tissue repair or storage. Organs like the liver, pancreas, and muscles work together to manage this energy surplus. In the starved state, things flip. Without food, blood sugar drops and insulin levels fall. The body taps into glycogen stores first, but after about 24 hours, those run low. Then, the liver starts gluconeogenesis, making glucose from non-carb sources like amino acids and glycerol. Meanwhile, ketogenesis ramps up, breaking down fats into ketone bodies for energy, especially for the brain. The liver and kidneys are key players here, with the kidneys handling some gluconeogenesis. For carb metabolism, it's all about glycolysis breaking down glucose for energy. In the fed state, glucose is king, fueling cells via ATP production. In starvation, the body spares glucose for the brain and red blood cells, relying more on ketones.
Okay, so I'll just put it as a general rule, guys, a prompt that I always put to Grok. Grok, remember, dude, we want to keep this back and forth going quite fast. So try to answer with the least amount of words, but make sure you are getting your point across. So just use your words effectively and efficiently. Okay, so I want to understand changes in metabolism from the absorptive state to the post-absorptive state.
Got it. Fast and efficient. In the absorptive state, after eating, insulin drives glucose uptake for energy or storage as glycogen and fat. Liver, muscles, and fat tissue sync up. In the post-absorptive state, 16 hours post-meal, insulin drops, glucagon rises. Glycogen breaks down, and gluconeogenesis starts in the liver to maintain blood sugar. Fats begin to break down for energy. Liver and kidneys lead the shift. Want me to dig into diabetes next?
Will amino acids also break down? Will amino acids also become proteins and then back to amino acids?
Yeah, amino acids are dynamic. In the absorptive state, they're used to build proteins for tissue repair or growth. In the post-absorptive or starved state, proteins can break down into amino acids to fuel gluconeogenesis, making glucose in the liver. It's a constant cycle, building up or breaking down based on energy needs. Want to tie this to diabetes or renal failure?
So I want to ask you about so the energy source for most cells are fatty acids in the post-absorptive state. Why?
In the post-absorptive state, most cells switch to fatty acids for energy because glucose is scarce. Glycogen stores deplete, so the body breaks down triglycerides into fatty acids via lipolysis. These fatty acids are oxidized for ATP, sparing glucose for the brain and red blood cells. Liver orchestrates this to keep energy flowing. Want to link this to diabetes or renal failure next?
I don't get why the fatty acids are the energy source in the post-absorptive state.
All right, let's break it down. In the post-absorptive state, 16 hours after eating, glycogen stores start running low, and glucose isn't coming in from food.
I see, that makes sense. Got it. Okay.
Cool.
So,
Glad it-
so insulin inhibits glucagon secretion. I didn't know this.
Yeah, it's a cool checks and balances thing. Insulin, high after eating, suppresses glucagon to prevent the liver from releasing extra glucose when blood sugar's already up. In the post-absorptive state, insulin drops, letting glucagon rise to boost glucose production. Pancreas keeps it tight. Want to dive into how this ties to diabetes?
How does it inhibit glucagon secretion?
Insulin inhibits glucagon secretion mainly through direct signaling in the pancreas. High insulin levels, post-meal, bind to receptors on alpha cells, dialing down glucagon release to stop excess glucose production in the liver. It's like insulin telling glucagon, chill, we've got enough sugar. Want to connect this to diabetes or move to renal failure?
Interesting. Okay. Why don't we talk a bit about them? So, why does the brain remain unchanged regarding glucose utilization, but the liver, muscle, and adipose tissue get affected with regard to what we were saying about insulin inhibiting glucagon secretion?
The brain keeps using glucose at a steady rate because it's super dependent on it and can't easily switch to other fuels, like fatty acids. It needs a constant supply, about 150 grams daily, regardless of fed or post-absorptive state. Insulin and glucagon don't directly mess with the brain's glucose uptake, since it's largely insulin independent. Meanwhile, liver, muscle, and adipose tissue are insulin sensitive. In the fed state, insulin promotes glucose uptake and storage and glycogen in liver and muscle.
So if it's insulin independent, then how does it work?
The brain's glucose uptake is insulin independent because it relies on glucose transporters, mainly GL1 and gluca3, which grab glucose from the blood without needing insulin. These transporters work based
Wait,
on...
which one is it?
My bad for the confusion. The brain primarily uses gluca1 for blood-brain barrier transport and gluca3 for neurons. Both are insulin independent, pulling glucose based on blood levels, not insulin signals. This keeps the brain fueled even when insulin's low. Clear now?
Excuse me, guys. GLUT1 and GLUT3. Okay. Let me ask you then. So,
No worries.
we have glycogen now after the conversion. Okay. So what's going on after the increase of insulin? We have the conversion to glycogen, but what's going on with triglycerol or whatever it's called? Why are they secreted as very low density lipoproteins? And some of it enters the TCA cycle. What's the point of that?
All right, let's unpack this. After a meal, insulin spikes, driving glucose into cells. In the liver, glucose is converted to glycogen for storage. Think of it as a quick access energy reserve. Excess glucose also gets turned into fatty acids, which combine with glycogen to form triglycerides. These triglycerides are packaged into very low density lipoproteins, VLDL, in the liver and secreted to transport fats to adipose tissue for long-term storage. It's like the body's way of stashing extra energy as fat when glycogen stores are full. Some glucose enters the TCA cycle, Krebs cycle, to produce ATP, the cell's energy currency, especially in active tissues like muscles. This happens when immediate energy is needed rather than storage.
I'm a bit confused, dude. I don't know how these fit together. This TCA cycle, the VLDL, the triglycerides, how do these fit to the idea of insulin increasing and glucose becoming glycogen?
No stress. Let's connect the dots. When insulin rises after eating, it pushes glucose into cells. In the liver, glucose is first stored as glycogen, quick energy for later. If there's extra glucose, the liver turns it into fatty acids, which combine with glycogen to make triglycerides. These triglycerides are packed into VLDL to ship to fat tissue for long-term storage.
Why
Meanwhile-
VLDL? And why do they go to the fat tissue?
VLDL is used because it's like a courier, carrying triglycerides from the liver to fat tissue for storage. After a meal, excess glucose turns into triglycerides in the liver. Since the liver can't store much fat, it packages triglycerides into VLDL to transport them through the blood to adipose tissue, where they're stored as body fat for long-term energy reserves. It's the body's way of saving extra calories when glycogen stores are full. Want to dive deeper into this or switch to diabetes?
Oh, that's fair enough. Okay. And
Cool.
then
All right.
and
So
then
let's
what's going on with excess amino acids? Why are they getting converted to pyruvate? From where to where? This is like this sounds like fake news to me. What's going on?
Excess amino acids get converted to pyruvate as a way to handle surplus protein when you eat more than needed for tissue repair or enzymes. After a meal, amino acids from dietary protein flood the bloodstream. The liver takes up the excess and, through deamination, strips off their nitrogen to form pyruvate or other intermediates. Pyruvate can then feed into gluconeogenesis to make glucose, stored as glycogen, or go to the TCA cycle for ATP.
That's
This
so
hap-
cool, dude. That's so cool.
Haha, glad you're pumped about it. It's wild how the body repurposes stuff like that. Want to keep going with this or pivot to diabetes or renal failure?
Why don't we talk a bit about so GLUT4 helps the glucose enter the muscle.
Yup, exactly. GLUT4 is key for getting glucose into muscle cells. When insulin levels rise after eating, it signals GLUT4 transporters to move to the muscle cell surface, pulling glucose in from the blood. This glucose is used for energy or stored as glycogen. Unlike the brain's GLUT1 and gluca3, GLUT4 is insulin dependent, so it's a big player in muscle and fat tissue. Want to link this to diabetes or something else? All right. So we were just on GLUT4, helping glucose get into muscle cells with insulin's help.
But
What's next?
and fatty acids, they enter the muscle via chylomicrons. What are these chylomicrons? And why is this the ideal way to enter? From the liver via VLDL. Why VLDL and not high HDL?
All right, let's clear this up. Fatty acids don't primarily enter muscles via chylomicrons. Chylomicrons are lipoprotein particles made in the intestine to transport dietary fats, triglycerides, from digested food to tissues like muscle and adipose after a meal. They deliver fatty acids via lipoprotein lipase, which breaks down triglycerides into free fatty acids for muscle use or storage. For fatty acids from the liver, they're packaged into very low-density lipoproteins, VLDL, not chylomicrons. VLDL carries triglycerides synthesized in the liver, from excess glucose or amino acids to muscles and fat tissue. Why VLDL and not HDL? VLDL is designed to transport triglycerides outward for storage or energy use, while HDL is more about scooping up excess cholesterol and returning it to the liver for processing. VLDL's structure is optimized for delivering large triglyceride loads, unlike HDL, which handles smaller cholesterol cargoes. This makes VLDL the go-to for fatty acid delivery from
And
the
then
liver.
beta oxidation turns them to acetyl-CoA, which helps produce ATP to support contraction. I don't understand this. Why beta oxidation does this?
Beta oxidation is how muscles break down fatty acids to fuel contractions. Once fatty acids enter muscle cells, from chylomicrons or VLDL, they're transported into mitochondria. There, beta oxidation chops fatty acids into 2 carbon units, forming acetyl-CoA. This acetyl-CoA enters the TCA cycle, driving ATP production, which powers muscle contractions. It's like cutting a big log into small pieces to burn for energy. Fatty acids are ideal because they yield tons of ATP, perfect for sustained muscle work, especially when glucose is low. Want to dig deeper or switch topics?
Okay. And glucose also enters the adipose tissue by insulin-dependent GLUT4 transport system. And then glycolysis and PDH will turn it to acetyl-CoA. And then to fatty acids, and then to triacylglycerol. Why? I don't get this arbitrary thing. Arbitrary looking thing.
Haha, I hear you. It can seem like a random process. Here's why it happens. When glucose enters adipose tissue via insulin-dependent GLUT4 after a meal, it's converted to acetyl-CoA through glycolysis and pyruvate dehydrogenase, PDH. In adipose cells, acetyl-CoA is used to synthesize fatty acids, which are then combined with glycerol to form triacylglycerol triglycerides. Why? The body's goal is to store excess energy. When glycogen stores in the liver and muscles are full, glucose gets funneled into fat production for long-term energy storage in adipose tissue. It's not arbitrary, it's the body's efficient way to save calories for later, like packing away leftovers. Clearer now? Want to tie this to diabetes or something else?
Not so good. And with the brain, we said GLUT1 and 3.
Yup, spot on. The brain uses GLUT1 for glucose transport.
And do we have glucose oxidation in the brain?
Yeah, the brain does oxidize glucose. It's its main fuel. Once glucose enters via GLUT1 and GLUT3, it undergoes glycolysis to produce pyruvate, which is converted to acetyl-CoA. This feeds into the TCA cycle in mitochondria, driving oxidative phosphorylation to churn out ATP. The brain burns through about 1,150 grams of glucose daily for energy. Want to explore more on this or jump to another topic?
But why does it need to oxidize it?
The brain oxidizes glucose because it's the most efficient way to generate ATP, the energy currency it needs to function. Neurons are super active, constantly firing signals, and they rely on ATP to power ion pumps, synapses, and other processes. Glucose oxidation via glycolysis, the TCA cycle, and oxidative phosphorylation produces way more ATP than other fuels. The brain can't easily use fatty acids due to the blood-brain barrier and its limited ability to process them, so glucose is king. It's like the brain's high-octane fuel for non-stop work. Clear? Want to keep going or switch gears?
No, that's so good. Let's not change topics necessarily, same field of topics, but let's do a shift in gears. And I want to ask you a bit more about carb metabolism. And I want to ask you about glycolysis. So with glycolysis, we have metabolism of glucose. We produce energy as ATP. G3P, pyruvate, acetyl-CoA, and then we also have regulation of glycolysis. And remind us how PFK1 and pyruvate kinase fit into all of this.
All right, let's zoom into glycolysis and carb metabolism. Glycolysis breaks down glucose to produce energy, happening in the cytoplasm of cells. Glucose is converted through several steps into 2 pyruvate molecules, netting 2 ATP and 2 NADH for energy. Key intermediates include glyceralpha 3-phosphate, G3P, which is further processed to pyruvate. If oxygen's around, pyruvate can become acetyl-CoA for the TCA cycle. Now, regulation. Phosphofructokinase 1, PFK1, and pyruvate kinase are critical control points. PFK1 is the main regulator, catalyzing the step where fructose 6-phosphate becomes fructose 1,6-bisphosphate. It's like the gatekeeper of glycolysis, revved up by high AMP, low energy, and slowed by high ATP or citrate, plenty of energy. Pyruvate kinase at the end converts phosphoenolpyruvate to pyruvate, producing ATP. It's activated by fructose 1,6-bisphosphate, feed-forward signal, and inhibited by ATP or alanine when energy's high. These enzymes fine-tune glycolysis to match the cell's energy needs. Want to dive deeper into regulation or connect this to diabetes?
So
So,
with glycolysis, we end up having pyruvate. What about the lactate? Is lactate anaerobic basically, and otherwise, in aerobic conditions, pyruvate goes to the TCA cycle, or have I gotten this completely wrong?
no worries, you're not completely off, just needs a quick tweak. You're right that glycolysis ends with pyruvate. What happens next depends on oxygen. In aerobic conditions, with oxygen available, pyruvate enters the mitochondria, gets converted to acetyl-CoA by pyruvate dehydrogenase, and feeds into the TCA cycle to produce more ATP. In anaerobic conditions, like during intense exercise when oxygen's scarce, pyruvate is converted to lactate by lactate dehydrogenase in the cytoplasm. This regenerates NAD plus needed to keep glycolysis running for ATP production.
Excuse me, so where was I don't understand what exactly you tweaked. Compare what I said with what you said.
No problem. Let's line it up. You said glycolysis ends with pyruvate, and in anaerobic conditions, pyruvate becomes lactate, while in aerobic conditions, pyruvate goes to the TCA cycle. That's mostly spot on. The tweak is just clarifying that lactate itself isn't anaerobic. It's produced in anaerobic conditions to keep glycolysis going by regenerating NAD+.
Okay, perfect. So with glycolysis, we have glucose broken down, and then we have pyruvate. And pyruvate forms glucose. I don't get it.
All right, let's clear this up. In glycolysis, glucose is broken down into two pyruvate molecules, producing a bit of ATP and NADH. This happens in the cytoplasm, no matter the oxygen level. Now, pyruvate doesn't form glucose directly. That's a different process called gluconeogenesis.
Yeah, I'm trying to compare glycolysis with gluconeogenesis. Because how come oxaloacetate helps form glucose but also results from the breakdown of glucose? It's like...
I get the confusion. It's like a metabolic loop messing with your head. Let's compare glycolysis and gluconeogenesis to clear it up, with a focus on oxaloacetate. Glycolysis breaks down glucose into two pyruvate molecules in the cytoplasm, making ATP and NADH. It's the energy now pathway, happening when glucose is plentiful. Pyruvate can then enter mitochondria, become acetyl-CoA, and feed the TCA cycle, where oxaloacetate is an intermediate. So, oxaloacetate shows up as part of glucose breakdown when pyruvate fuels the TCA cycle. Gluconeogenesis, on the other hand, is the opposite. It builds glucose from non-carb sources like pyruvate, lactate, or amino acids, mainly in the liver, when glucose is scarce, like during fasting. Pyruvate is converted to oxaloacetate in mitochondria, then to phosphoenol pyruvate, and eventually to glucose through a series of steps. Here, oxaloacetate is a key starting point for making glucose. Why the overlap? Oxaloacetate is like a metabolic hub. It's part of both breakdown, TCA cycle from glycolysis, and synthesis, gluconeogenesis, to make glucose. The direction depends on the body's needs.
So how do we make the glucose? I don't get it.
All right, let's zoom in on how gluconeogenesis makes glucose, since that's where the confusion is. When your body needs glucose, like during fasting or low-carb states, gluconeogenesis kicks in, mainly in the liver and a bit in the kidneys. It starts with non-carb precursors like pyruvate, lactate, glycerol, or amino acids. Here's the quick rundown. Pyruvate, from lactate or amino acids, is converted to oxaloacetate in the mitochondria using the enzyme pyruvate carboxylase. Oxaloacetate is then turned into phosphoenol pyruvate by another enzyme. From there, a series of enzyme-driven steps reverse parts of glycolysis, eventually forming glucose. Glycerol.
That's so cool. Who knew?
Right? It's like the body's secret chemistry lab. Want to keep digging into gluconeogenesis or pivot to something like diabetes or renal failure?
Why don't we talk about the urea cycle?
All right, let's shift to the urea cycle.
Well, because increased rates of gluconeogenesis are coupled with increased rates of urea synthesis. Maybe we can understand it.
Nice connection. You're right. Gluconeogenesis and the urea cycle are linked, especially when protein breakdown ramps up. Here's the deal. Gluconeogenesis makes glucose from non-carb sources like amino acids in the liver, often during fasting or starvation. When amino acids are used, their nitrogen groups are removed via deamination, producing ammonia, which is toxic. The urea cycle kicks in to convert this ammonia into urea, a safer compound excreted by the kidneys. So, higher gluconeogenesis of more amino acid breakdown means more ammonia, which drives increased urea synthesis to keep things detoxified. It's like a cleanup crew working overtime when the body's recycling protein for glucose. Clear? Want to dive deeper into the urea cycle steps or link this to renal failure?
So ammonia is toxic. We have to eliminate it. So we convert it to urea.
Exacto. El amoníaco es
Okay,
tóxico.
and so I see. So we use the amino acids for glucose, but they have to lose their ammonia first. So we have the extra ammonia, and so it's converted to urea. Okay. Wow, so cool. What about fumarate?
Nice catch. Fumarate pops up in both the urea cycle and the TCA cycle, tying things together. In the urea cycle, which detoxifies ammonia into urea in the liver, fumarate is produced as a byproduct when argininosuccinate is split into arginine and fumarate. This fumarate can then shuttle to the TCA cycle, where it's converted to malate and eventually oxaloacetate, which can feed into gluconeogenesis to make glucose. So, when gluconeogenesis ramps up using amino acids, the urea cycle generates fumarate, which supports glucose production indirectly. It's like a metabolic bridge between detoxing ammonia and making glucose. Want to dive deeper into this link or explore something else?
I want to understand oxaloacetate is exactly the same thing as a pyruvate.
Okay, let's clear this up. Oxaloacetate and pyruvate are not the same, but they're closely related in metabolism. Pyruvate is a 3-carbon molecule produced from glucose via glycolysis in the cytoplasm. Oxaloacetate, a 4-carbon molecule, is a key intermediate in the TCA cycle and gluconeogenesis, mainly in mitochondria. Here's how they connect. Pyruvate can be converted to oxaloacetate by the enzyme pyruvate carboxylase in the liver, adding a carbon from CO2 to pyruvate. This happens during gluconeogenesis to make glucose from pyruvate, or when the TCA cycle needs replenishing. So, pyruvate is like a precursor that can turn into oxaloacetate, but they're distinct molecules with different roles. Clear now? Want to explore their roles more, or jump to
What's
another
their
topic?
differences?
All right, let's break down the differences between pyruvate and oxaloacetate. 1. Structure. Pyruvate is a 3-carbon molecule, C3H4O3, a simple keto acid from glycolysis. Oxaloacetate is a 4-carbon molecule, C4H4O5, a keto diacid in the TCA cycle and gluconeogenesis. 2. Location. Pyruvate is mainly produced in the cytoplasm during glycolysis. Oxaloacetate is primarily in mitochondria, where it's formed or used in the TCA cycle or gluconeogenesis. 3. Role. Pyruvate is the end product of glycolysis, used for energy, converted to acetyl-CoA for TCA cycle in aerobic conditions, or lactate in anaerobic conditions. Oxaloacetate is a TCA cycle intermediate that helps generate ATP and a starting point for gluconeogenesis to make glucose from non-carb sources. 4. Formation. Pyruvate comes from glucose breakdown. Oxaloacetate can be made from pyruvate via pyruvate carboxylase, adding a carbon, or from TCA cycle intermediates like malate. 5. Function in metabolism. Pyruvate is a fuel source or precursor.
Okay. Don't forget, dude. For this podcast, for the next 200 messages, we need to keep our answers short. Use the least amount of words to get our point across, using words effectively and efficiently. Having said that, let's talk a bit about PFK1 and why it's subject to energy-dependent allosteric regulation by ATP, AMP, and protons. H plus, yeah.
Right. PFK1 regulates glycolysis by catalyzing fructose 6-phosphate to fructose 1,6-bisphosphate. It's allosterically controlled. ATP inhibits it when energy's high, slowing glycolysis. AMP activates it when energy's low, boosting glycolysis. Protons, low pH, inhibit it, preventing excess lactate and acidic conditions. This tunes glycolysis to cell energy needs. Want to dive deeper or switch topics?
I don't get this concept, to be honest.
No worries. PFK1 is like a glycolysis throttle. High ATP means the cell's energy rich, so PFK1 slows glycolysis. High AMP signals low energy, so PFK1 speeds it up. Low pH, more protons from lactate buildup, also slows PFK1 to avoid acid overload. It's all about balancing energy production. Clearer? Want more on this?
I don't really get it. So it prevents glucose being utilized by glycolysis when ATP is available because it binds in a cheeky way. And ATP does this?
Close. Let's simplify. PFK1 controls glycolysis speed. When ATP is high, it binds to PFK1's allosteric site, not a GQA, and inhibits PFK1. This slows glycolysis since the cell doesn't need more.
Again.
My bad if I slipped up. I think you mean keeping answers
No,
short.
tell me again. I didn't get that.
All right, super clear and short. PFK1 controls glycolysis. High ATP binds PFK1's allosteric site, inhibiting it, slowing glycolysis since energy is plentiful. Low ATP or high AMP activates
So
PFK.
ATP will inhibit ATP.
Not quite. ATP
But
doesn't
this is
inhibit.
what you're saying to me. You're saying ATP will inhibit PFK1, which inhibits the use of ATP.
I see the mix-up. Let's clarify. High ATP inhibits PFK1, which slows glycolysis. This doesn't inhibit ATP use it, reduces ATP production via glycolysis, because the cell already has enough ATP. PFK1 acts like a brake to avoid overproducing energy. Clear now?
And the ATP itself does this.
Yep, ATP itself does this.
And what
When
does AMP do then? The opposite.
Exactly. AMP does the opposite. When AMP is high, signaling low energy, it binds PFK1's allosteric site, activating it to speed up glycolysis and make more ATP.
ATP and AMP. Okay, fair enough. Let's continue. Let's talk a bit about the early fasting state again. So here, glucose falls. It doesn't enter the GLUT2 transporter now. So now liver will start exporting glucose instead. Up to now we understand more glucagon, etc., etc. So how does CAMP play a role in this is my question.
All right, back to it. In early fasting, blood glucose drops. Less enters liver via GLUT2. Glucagon rise.
Yeah, keep going. Why you stop?
Got it. Glucagon spikes CAMP in liver cells, activating protein kinase A. pKa triggers glycogenolysis, breaking glycogen into glucose for export, and gluconeogenesis, making new glucose from lactate and amino acids. CAMP is the signal flipping the liver to glucose production mode. Clear? Want more on this?
I wonder why CAMP is a 1.
Good question. CMP is the messenger because it's fast and effective. Glucagon binds liver receptors, activating adenylate cyclase, which makes CMP. CMP then triggers protein kinase A to kickstart glycogenolysis and gluconeogenesis.
And also
It's like
protein is broken down. Amino acids fuel gluconeogenesis, fatty acids from lipolysis, we said, are used to produce energy via beta oxidation. I've got so many things and it's so weird to me.
I feel ya. It's a lot to juggle. Let's simplify. In early fasting, protein breaks down into amino acids, fueling gluconeogenesis in the liver to make glucose. Meanwhile, lipolysis releases fatty acids from fat stores, which undergo beta oxidation in muscles and other tissues to produce ATP via acetyl-CoA and the TCA cycle. It's the body's teamwork liver makes. Glucose, fatty acids power other cells to keep energy flowing when food's scarce. Clearer? Want to focus on one part?
Interesting. So now when we don't have glucose in the muscle, we will have fatty acid oxidation. Why do we need oxidation to get energy? I don't get it.
In muscles during early fasting, glucose is low, so fatty acids from lipolysis become the main fuel. Beta oxidation breaks them down in mitochondria to acetyl-CoA, which enters the TCA cycle to produce ATP. Oxidation is needed because it efficiently extracts energy from fatty acids' chemical bonds, generating lots of ATP to power muscle activity. It's like burning high-energy fuel when sugar's gone. Clear? Want more on this?
Yes, I do.
Cool. Let's dig deeper. Beta oxidation in muscles chops fatty acids into acetyl-CoA, fueling the TCA cycle for ATP. This process yields more ATP per molecule than glucose oxidation, making fatty acids a powerhouse for sustained energy during fasting. Each step strips electrons, driving the electron transport chain for max ATP. Want to focus on a specific step or connect to another topic?
So, tell me one more time this.
All right, one more time. In fasting, muscles lack glucose, so fatty acids from fat breakdown are used. Beta oxidation in mitochondria splits fatty acids into acetyl-CoA, which feeds the TCA cycle to crank out ATP. It's a high-yield process, giving muscles tons of energy when sugar's low. Got it?
Okay, let's shift again. Let's talk a bit about energy metabolism for muscle contraction. So we have ATP. We have ATPase activity. And so ATP supplies the ATPase activity of myosin.
All right, let's dive into energy metabolism for muscle contraction. ATP powers muscle movement by fueling myosin ATPase. Myosin's ATPase activity splits ATP into ADP and energy, driving the myosin head to pull actin filaments, causing muscle contraction. ATP is mainly from glycolysis, fast, glucose-fueled, or oxidative phosphorylation, slower, from fatty acids or glucose via TCA cycle. In fasting, beta oxidation of fatty acids ramps up for ATP. Clear? Want to focus on a specific part?
No, that's okay. So,
Cool.
okay. And then we have muscle metabolism. Let's talk about muscle metabolism at rest, though. So we don't have a lot of lactate produced. Pyruvate is used for glycogen synthesis specifically, or used in the TCA cycle. Yeah, that makes sense. We've talked about these things today. We have sufficient oxygen. Okay, up to now this makes sense.
Nice. Your time tying it together. At rest, muscle metabolism is chill. With enough oxygen, pyruvate from glycolysis mostly enters the TCA cycle for ATP via oxidative phosphorylation.
And then we have muscle metabolism in exercise. It will be a bit different, right? Tell us about like nitric oxide and beta adrenergic stimulation of vascular smooth muscles, how they increase blood flow, and now the amount of energy from glycolysis, and how does it change during exercise, I guess is what I'm asking.
All right, muscle metabolism during exercise shifts gears. Glycolysis ramps up to quickly produce ATP, especially in intense exercise, leading to pyruvate converting to lactate when oxygen's limited, lactate acid buildup. Beta adrenergic stimulation, triggered by adrenaline, activates vascular smooth muscle, relaxing blood vessels via CMP to boost blood flow, delivering more oxygen and glucose. Energy from glycolysis surges for fast ATP, but oxidative phosphorylation from fatty acids and glucose via TCA cycle also kicks in for sustained effort. Lactate can shuttle to the liver for gluconeogenesis later. It's a high-speed switch to fuel muscle demand. Clear? Want to zoom in on any part?
Fair enough. Okay, so tell me about glycogen synthase and phosphorylase. So glycogen synthase, what's going on with G6P? It's low during exercise. And tell me also about, okay, yeah, let's talk about glycogen synthase and phosphorylase. I'll give it to you, the mic.
All right, mic's on. Glycogen synthase and glycogen phosphorylase control glycogen in muscles. Glycogen synthase builds glycogen, sticking glucose units together, activated when glucose 6-phosphate, G6P is high, rest, fed state. During exercise, G6P drops as glycogen surges, so synthase slows. Glycogen phosphorylase breaks glycogen into glucose 1-phosphate for quick energy, ramped up by adrenaline and low G6P during exercise. It's a tag team. Synthase stores at rest, phosphorylase releases during action. Clear? Want more details?
Yes, I didn't understand anything.
No stress. Let's simplify. Glycogen synthase makes glycogen in muscles when glucose 6-phosphate, G6P is high, like at rest after eating. During exercise, G6P is low because it's used in glycolysis, so synthase shuts off. Glycogen phosphorylase does the opposite. It breaks glycogen into glucose for energy during exercise, triggered by adrenaline and low G6P. Synthase is storage. Phosphorylase release. Got it? Want to retry any part?
Kind of get now, yeah. Okay. So, okay.
Sweet. Glad it's clicking. What's next?
So, beta-2 adrenoreceptors result in vasodilation. Why?
Beta-2 adrenergies cause vasodilation because adrenaline binds them on vascular smooth muscle, activating adenylate cyclase. This raises CNP, which triggers protein kinase A to relax muscle by lowering calcium levels. Relaxed vessels widen, boosting blood flow to muscles during exercise or stress. It's like opening a highway for oxygen delivery. Clear? Want more on this?
Yes.
All right. Beta-2 adrenergies on vascular smooth muscle get hit by adrenaline, sparking adenylate cyclase to produce CNP. CNP activates protein kinase A, which cuts calcium in muscle cells, causing relaxation. This widens blood vessels, ramping up blood flow to deliver more oxygen and nutrients, especially during exercise. Want to dig into CNP's role or something else?
I don't get it.
No worries. Let's break it down simpler. Adrenaline hits beta-2 adrenergies on blood vessel muscles. This boosts CNP, which tells the muscle to relax by lowering calcium. Relaxed muscle means wider vessels, so more blood flows to muscles for oxygen and energy during exercise. It's like flipping a switch to open the pipes. Clear now?
Yeah, that kind of makes sense. Okay, I think this is a good time to start talking a bit about diabetes. So we lack insulin in type 1, and mellitus means basically sweet or something.
Nice pivot. Yeah, in type 1 diabetes, the body doesn't make insulin due to autoimmune destruction of pancreatic beta cells. Mellitus comes from Latin, meaning sweet, because high blood sugar spills into urine, making it sweet tasting. Old school diagnosis. Without insulin, glucose can't enter cells, so blood sugar skyrockets. Want to dive into how this messes with metabolism or compare to type 2?
Well, I want to understand. So beta cells, we have autoimmune destruction of beta cells. Why not alpha cells? Are beta cells, what do alpha cells do? In the islets of Langerhans.
Islets of Langerhans do sound fancy. Beta cells in the islets make insulin, which lowers blood sugar by pushing glucose into cells. Alpha cells produce glucagon, which raises blood sugar by triggering glucose release from the liver. In type 1 diabetes, the immune system mistakenly targets beta cells, not alpha cells, likely due to specific antigens on beta cells triggering the attack. Why beta and not alpha? It's not fully clear, but beta cells seem more vulnerable to autoimmune misfires. Alpha cells keep chugging, so glucagon still works, which can
What is
worsen.
alpha cells? I don't know what alpha cells is, dude.
My bad for jumping ahead. Alpha cells are in the pancreatus islets of Langerhans. They make glucagon, a hormone that raises blood sugar by telling the liver to release stored glucose or make new glucose.
And we have no feedback inhibition by insulin on alpha cells, so we have glucagon excess. Is this going to be a problem?
Yup, you nailed it. In type 1 diabetes, without insulin from beta cells, there's no feedback to suppress alpha cells, so glucagon runs wild. This is a problem because excess glucagon tells the liver to pump out glucose via glycogenolysis and gluconeogenesis, spiking blood sugar even more. It's like a gas pedal stuck on high with no brakes. Want to dive into how this affects metabolism or treatment?
Yeah, let's do it.
All right. With no insulin to check glucagon in type 1 diabetes, glucagon overdrives the liver to release glucose, spiking blood sugar. This ramps up glycogenolysis and gluconeogenesis, while lipolysis floods the blood with fatty acids, leading to ketone production and possible ketoacidosis. Treatment involves insulin injections to restore balance, suppress glucagon, and let cells use glucose. Want to focus on ketoacidosis or insulin therapy? So, we were just on how excess glucose...
So what's going on with... So lactate and amino acids like alanine from protein breakdown, these are going to be substrates for glucose production, basically.
Exactly. In type 1 diabetes with glucagon unchecked, the liver uses lactate and amino acids like alanine from muscle protein breakdown as substrates for gluconeogenesis to make glucose. This ramps up blood sugar since insulin isn't there to stop it or push glucose into cells. It's like the liver's stuck in overdrive. Want to dive into how this ties to ketoacidosis or something else?
I don't get it.
No worries. In type 1 diabetes, no insulin means glucagon runs free. This makes the liver use lactate and amino acids, like alanine from broken down muscle protein, to fuel gluconeogenesis, churning out extra glucose.
But why do we need extra glucose? We have so much in the blood all the time.
Great question. In type 1 diabetes, even though blood sugar is high, cells can't use it because there's no insulin to shuttle glucose into them. The body thinks it's starving, so glucagon signals the liver to make more glucose via gluconeogenesis, using lactate and amino acids like alanine. It's a miscommunication, too much glucose in the blood, but none reaching cells for energy. Want to explore why this leads to ketoacidosis
I don't
or
get
another?
it, bro. I didn't get your answer to what I asked.
My bad, let's nail it. You asked why the body makes extra glucose when blood sugar's already high in type 1 diabetes. The issue is, without insulin, cells can't access the glucose in the blood. They're starving.
I see. Okay. So, what about fatty acids from lipolysis? Yeah, they are also going to support gluconeogenesis. I see. And what about the acetyl-CoA? Will it become ketone? And yeah, explain what's going on there and how it leads to ketoacidosis maybe. And yeah, will they help with gluconeogenesis or no?
All right, let's connect it. In type 1 diabetes, no insulin triggers lipolysis, releasing fatty acids. These don't directly fuel gluconeogenesis. Glycerol from triglycerides does that. Instead, fatty acids go to the liver, where beta oxidation turns them into acetyl-CoA. With glucose unused due to no insulin, the liver converts excess acetyl-CoA into ketones for energy. High ketones can lead to ketoacidosis, dropping blood pH dangerously. So, fatty acids indirectly worsen the crisis by flooding ketones, not aiding gluconeogenesis much. Clear? Want more on ketoacidosis?
I don't get it.
Okay, let's simplify. In type 1 diabetes, no insulin causes fat breakdown, lipolysis, releasing fatty acids. These go to the liver, where beta oxidation makes acetyl-CoA. The liver turns excess acetyl-CoA into ketones, not glucose. Only glycerol from fats helps gluconeogenesis. Too many ketones cause ketoacidosis, making blood acidic. Fatty acids fuel ketones, not gluconeogenesis directly. Got it? Want to focus on ketoacidosis?
I still don't get it.
No stress. Let's try again. In type 1 diabetes, no insulin triggers fat breakdown, releasing fatty acids. The liver turns these into acetyl-CoA via beta oxidation. Instead of making glucose, gluconeogenesis uses glycerol, not fatty acids. The liver converts acetyl-CoA into ketones. Excess ketones build up, causing ketoacidosis, which makes blood too acidic. Fatty acids
What do
drive
ketones do though?
Ketones are backup fuel. In type 1 diabetes with no insulin,
But since it's fuel, doesn't mean they're going to be used. So how can we have ketoacidosis if they're going to be used?
Great point. Ketones are made as backup fuel when glucose can't be used due to no insulin in type 1 diabetes. The problem is, ketones are produced faster than tissues, like the brain or muscles, can use them, especially since insulin's absence limits their efficient uptake. This flood of ketones builds up in the blood, lowering pH and causing ketoacidosis, a dangerous acidic state.
So they build up faster than we can use them.
Exactly.
Okay.
In type ketone bodies, acetoacetate, beta hydroxybutyrate, acetone, form in the liver from fatty acids during low insulin, like in type 1 diabetes. Beta oxidation turns fatty acids into acetyl ketone. Two acetyl ketone molecules combine to make acetoacetyl ketone, then HMG-CoA synthase forms HMG-CoA, which is cleaved to acetoacetate. Non-enzymatic decarboxylation happens when acetoacetate spontaneously loses CO2, forming acetone, minor ketone, gives fruity breath. Meanwhile, beta-hydroxybutyrate diagnostics converts acetoacetate to beta-hydroxybutyrate, the main ketone in blood, using NADH. This ramps up in fasting or diabetes when glucose is unusable. Clear? Want more on ketoacidosis impact?
That's good. Okay. Let's jump back now to the fasting state and let's focus on adipose tissue. So we have glucose entering the adipose tissue with a GLUT4 transport system. And it's reduced because of the lowered insulin. And we have lower insulin, early fasting state. Yeah, that makes sense. Sorry guys, sorry. I know this is not in a form of a question really. I'm just trying to understand this topic myself. So what's going on with triglycerides in this situation? Are they mobilized? What does mobilization mean?
No worries. Love the enthusiasm. In early fasting, adipose tissue sees less glucose uptake via GLUT4 because insulin is low. This shifts gears. Triglycerides in adipose are mobilized, meaning hormone-sensitive lipase, activated by high glucagon, low insulin, breaks them down into glycerol and fatty acids. Glycerol goes to the liver for gluconeogenesis, making glucose. Fatty acids head to tissues like muscle for beta oxidation, producing ATP, or to the liver for ketone production.
I see what you mean. Yeah, this makes a lot of sense. We start giving the jobs to do. Okay. Yeah, that makes sense. And the brain doesn't switch to fatty acids. Why is the brain so picky?
The brain's a diva. It doesn't switch to fatty acids because the blood-brain barrier blocks most fatty acids from entering, and neurons lack enzymes for efficient fatty acid breakdown. The brain needs glucose or ketones, which it can use during fasting for energy, as they're small enough to cross the barrier and provide quick ATP. It's picky to keep its high energy demands met reliably. Clear? Want more on brain metabolism?
Okay, so so the brain is a diva, you were saying. Explain this a bit more, why it only takes glucose and it doesn't accept fatty acids. And yeah.
All right, back to the medicine. The brain's picky because it mainly uses glucose for energy. Glucose crosses the blood-brain barrier via GLUT1 and GLUT3 transporters, providing quick ATP through glycolysis and the TCA cycle. Fatty acids don't work well since the barrier blocks most of them, and brain cells lack enzymes to efficiently oxidize them. During fasting, the brain can use ketones from fatty acid breakdown, but glucose is king for its speed and reliability.
Okay, what's going on with thyroid hormones and when we're starved? Why do we have a decrease?
In starvation, thyroid hormone levels, especially T3, drop to conserve energy. The body downregulates thyroid hormone production via the hypothalamus, pituitary, thyroid axis, reducing metabolic rate. Less T3 means slower metabolism, sparing glucose and fat stores for vital organs like the brain. It's like dimming the body's engine to save fuel. Clear? Want more on thyroid or starvation?
Tell me a bit more about this. I don't understand why we have decrease in thyroid hormones.
No problem. During starvation, the body senses low energy and cuts thyroid hormone production, mainly T3, to slow metabolism. The hypothalamus reduces TRH, which lowers TSH from the pituitary, decreasing thyroid gland activity. Less T3 reduces energy use, preserving glucose and fat for critical needs, like brain function. It's a survival trick to stretch limited resources. Clear?
Okay, that makes sense. Okay, let's go back to diabetes then.
Cool. Back to diabetes. What's the angle you want to hit? Type 1, type 2, or something specific like ketoacidosis or insulin therapy?
So we have low insulin or no insulin or whatever, and this enhances lipolysis, which we explained why. What's going on in the plasma and urine then? So we have this hyperglycemia. We have a lot of glucose being peed in glycosuria or whatever it's called. And we're thirsty too, because we pee a lot of glucose. So what's going on then? So why is fatty acid synthesis greatly diminished in the diabetic state?
All right, let's unpack this. In type 1 diabetes with no insulin, lipolysis ramps up, flooding plasma with fatty acids and glycerol. Hyperglycemia, high blood glucose, happens because glucose can't enter cells, leading to glycosuria, glucose in urine, as kidneys can't reabsorb it all. This pulls water out, causing frequent urination and thirst, dehydration. Fatty acid synthesis is diminished because insulin, which normally activates it, is absent. Without insulin, the liver favors fat breakdown, lipolysis, and ketone production over synthesizing new fatty acids. It's like the body's stuck in breakdown mode, not storage.
I don't get this.
No stress. Let's simplify. In type 1 diabetes, no insulin causes high blood sugar, hyperglycemia. Kidneys spill glucose into urine, glycosuria, pulling water, so you pee a lot and get thirsty. Lipolysis spikes, raising plasma fatty acids, but fatty acid synthesis tanks because insulin, which drives fat making, is missing. The body breaks down fat instead of storing it. Clear now? Want to zoom in on any part?
Okay, let's talk a bit about the glucose fatty acid cycle, though. So let's say we have excess acetyl-CoA, and it's converted into citrate. Explain this conversion. And then this buildup inhibits PFK1, and I wonder why.
All right. Glucose fatty acid cycle it is. In excess, acetyl-CoA from fatty acid beta oxidation combines with oxalacetate to form citrate in the TCA cycle. High citrate spills into the cytoplasm, inhibiting PFK1, a key glycolysis enzyme. Why? Citrate signals energy abundance, telling PFK1 to slow glycolysis, favoring fatty acid use over glucose to balance energy sources. It's like a metabolic switch prioritizing fat burning. Clear?
No, I don't get the reason this happens.
No worries. High citrate from excess acetyl-CoA, fatty acid breakdown, inhibits PFK1 because it signals the cell has plenty of energy. This slows glycolysis, so the body uses fatty acids instead of glucose.
I see. Interesting.
So we were just saying high citrate slows glycolysis to save glucose. Want to dive deeper into the glucose fatty acid cycle, or jump back to something else like diabetes?
But so ketone bodies, they can be used in the brain, but not completely replace glucose.
Right. Ketone bodies, like beta-hydroxybutyrate, can fuel the brain during fasting or diabetes, crossing the blood-brain barrier to produce ATP via the TCA cycle. But they can't fully replace glucose because some brain processes, like certain neurotransmitter synthesis, strictly need glucose. Clear? Want to dig into ketones more?
Tell us more about this blood-brain barrier.
The blood-brain barrier is a tight layer of endothelial cells lining brain capillaries, controlling what enters the brain. It lets small molecules like glucose and ketones pass via transporters, GLT1, MCTs, but blocks most fatty acids due to size and lack of transporters, protecting the brain while ensuring fuel supply. Clear? Want more on its role?
I see. Okay, explain us more about the enzymes that are subject to allosteric control then during this glycogenolysis, glycogen synthesis situation.
In glycogenolysis and glycogen synthesis, key enzymes face allosteric control. Glycogen phosphorylase breaks glycogen into glucose 1-phosphate, is activated by AMP, low energy, and inhibited by glucose 6-phosphate, G6P and ATP, high energy. Glycogen synthase builds glycogen, is activated by G6P, signaling glucose abundance, and inhibited by glycogen itself. This balances glycogen breakdown and storage based on energy needs. Clear? Want to zoom in on one enzyme?
Tell me again which enzymes are, yeah.
Glycogen phosphorylase breaks glycogen, is activated by AMP, inhibited by G6P, ATP. Glycogen synthase makes glycogen, is activated by G6P, inhibited by glycogen. They balance glycogen use and storage. Clear? Want specifics on one?
That makes sense. Yeah, tell us a sentence for each.
Glycogen phosphorylase breaks glycogen into glucose 1-phosphate, revved by AMP, blocked by G6P and ATP. Glycogen synthase builds glycogen, boosted by G6P, slowed by glycogen itself.
I see. Okay, let's talk a bit about reciprocal regulation of phosphorylase and glycogen synthase by phosphorylation.
Glycogen phosphorylase and glycogen synthase are reciprocally regulated by phosphorylation. Phosphorylation, via protein kinase A, triggered by glucagon or adrenaline, activates phosphorylase, promoting glycogen breakdown, while it inactivates synthase, halting glycogen synthesis. Dephosphorylation, by protein phosphatase, flips it, activating synthase and inhibiting phosphorylase. This ensures glycogenolysis and synthesis don't happen simultaneously.
And glucagon and adrenaline, they increase CAMP production and they activate CAMP PK. And it's very confused with CAMP because at other times we decrease and the other times we increase it in different parts of the body and we have different effects.
You're right. CAMP's role can seem tricky. Glucagon and adrenaline boost CAMP in specific cells like liver or muscle, activating protein kinase A, PKA. In glycogen regulation, high CAMP PKA, phosphorylase glycogen phosphorylase turning it on, and glycogen synthase turning it off, favoring glycogen breakdown. Elsewhere, CAMP's effects vary. In fat cells, it triggers lipolysis. In smooth muscle, it causes relaxation. The outcome depends on the cell type and its enzymes. No confusion, it's context-specific signaling. Clear? Want to dive deeper into CAMP's roles?
Explain it a bit more.
CAMP acts as a messenger, but its effects depend on the cell. Glucagon or adrenaline bind receptors, raising CAMP via adenylate cyclase. In liver, muscle, CAMP activates PKA, which phosphorylates glycogen phosphorylase, on, breaks glycogen, and glycogen synthase, off, stops synthesis. In adipose tissue, CAMP PKA triggers lipolysis. In vascular smooth muscle, CAMP promotes relaxation. Same molecule, different targets, based on cell-specific enzymes and receptors. Clear? Want to focus on one tissue?
One more time.
CAMP's job changes by cell. Glucagon, adrenaline spikes CAMP, activating PKA. In liver, muscle, PKA phosphorylates glycogen phosphorylase, on, glycogen breakdown, and synthase, off, no glycogen buildup. In fat cells, CAMP PKA drives lipolysis. In smooth muscle, CAMP causes relaxation. It's one signal, but cell-specific enzymes dictate the outcome. Got it? Pick a tissue to zoom in.
Yeah, that makes sense. And how exactly does CAMP do this?
CAMP works by binding to protein kinase A, PKA, causing its activation. Glucagon or adrenaline triggers adenylate cyclase to make CAMP from ATP. CAMP binds PKA's regulatory subunits, releasing its catalytic subunits to phosphorylate targets like glycogen phosphorylase, activates glycogenolysis or glycogen synthase, inhibits synthesis in liver, muscle, or other proteins in different cells, driving cell-specific responses. Clear? Want to explore pKa targets?
I want to understand phosphorylase kinase. So it exists in an A and B form. The phosphorylated form is the active A form. And then phosphorylase kinase phosphorylase, switching it on. And then glycogen degradation at the same time. And it allows glycogen degradation at the same time. And it inhibits glycogen synthesis. You have to explain this to us.
All right, let's unpack phosphorylase kinase. It exists in two forms: inactive, E, and active, A, phosphorylates by pKa when CAMP is high from glucagon adrenaline. Active phosphorylase kinase phosphorylates glycogen phosphorylase, switching it to its active form to break down glycogen into glucose 1-phosphate, glycogenolysis. At the same time, pKa also phosphorylates glycogen synthase, inactivating it to block glycogen synthesis.
Step by step, we're stupid. At least I am. Tell me step one. So phosphorylase kinase is in A form. Phosphorylates phosphorylase. Why does phosphorylase need phosphorylation in the first place?
Step 1. Phosphorylase kinase, active A form, phosphorylated by pKa, phosphorylates glycogen phosphorylase. Glycogen phosphorylase needs phosphorylation to switch from inactive to active form, enabling it to break glycogen into glucose 1-phosphate for energy.
What the fuck?
I feel the confusion. Let's retry. Step 1. Phosphorylase kinase, active when phosphorylated, adds a phosphate to glycogen phosphorylase. This phosphorylase turns phosphorylase on, letting it chop glycogen into glucose for energy. Clear now? Next step?
Yes.
Cool. Step 2. Active glycogen phosphorylase, now phosphorylase, breaks glycogen into glucose 1-phosphate, which fuels glycolysis for energy. Meanwhile, pKa also phosphorylates glycogen synthase, turning it off to stop glycogen synthesis.
Wait, tell me this again.
No prob. Step 2. Phosphorylase glycogen phosphorylase actively breaks glycogen into glucose 1-phosphate, feeding glycolysis for energy. At the same time, pKa phosphorylase glycogen synthase, shutting it off so no glycogen is made.
I don't get this part.
Alright, let's simplify step 2. Once glycogen phosphorylase is turned on, phosphorylated, it cuts glycogen into glucose 1-phosphate, which the body uses for energy via glycolysis. Meanwhile, pKa adds a phosphate to glycogen synthase, turning it off to prevent glycogen buildup.
Well, I got the first part, so it breaks things down to glucose phosphate, and then what happens?
Got it. In step 2, active glycogen phosphorylase breaks glycogen into glucose 1-phosphate. This glucose 1-phosphate is converted to glucose 6-phosphate, which enters glycolysis to produce ATP for energy, especially in muscles or the liver during fasting.
I don't get this.
No worries, let's break it down. Glycogen phosphorylase, when active, chops glycogen into glucose 1-phosphate. This gets quickly turned into glucose 6-phosphate, which feeds into glycolysis, making ATP energy.
Oh man, I don't get it. Explain it from a different angle.
Alright, new angle. Think of glycogen as a candy jar full of glucose. Active glycogen phosphorylase is like a scoop that grabs glucose 1-phosphate pieces from the jar. Those pieces turn into glucose 6-phosphate, which the cell burns in glycolysis to make ATP, the energy cache for muscles or liver when you're low on sugar. Clear?
Yeah, but what happens after?
After glycogen phosphorylase makes glucose 1-phosphate, it's converted to glucose 6-phosphate. In the liver, glucose 6-phosphate can become free glucose for blood sugar. In muscles, it enters glycolysis, producing ATP for energy. Meanwhile, glycogen synthase stays off, so no glycogen is rebuilt. Clear?
Okay.
Next step?
Fair enough, yeah. So then, okay, insulin activates protein phosphatase, which removes the phosphates from phosphorylase.
Exactly. Insulin triggers protein phosphatase, which dephosphorylates glycogen phosphorylase,
And it
turning
switches
it.
off the glycogen breakdown.
Yup. Insulin activated protein phosphatase removes the phosphate from glycogen phosphorylase, switching it off, halting glycogen breakdown, and favoring glucose storage. Clear? Next part?
That makes sense. Okay, let's go back to just a sec, guys. Yeah, let's talk a bit about producing ATP then. So we've talked about aerobic and anaerobic. I didn't know that anaerobic is faster, but it's basically just less ATP.
Nice pivot. Yeah, anaerobic glycolysis is faster but produces less ATP. It quickly breaks glucose to pyruvate, making 2 ATP without oxygen, turning pyruvate to lactate. Aerobic respiration, glycolysis plus TCA cycle plus electron transport, is slower but yields 36 ATP by fully oxidizing glucose with oxygen. Speed versus quantity trade-off. Clear? Want to dive deeper?
So how does creatine work when I take it as a supplement?
Creatine supplements boost muscle energy. In muscles, creatine is phosphorylated to phosphocreatine, which rapidly donates a phosphate to ADP, regenerating ATP during high-intensity exercise like sprinting. This extends ATP availability before glycolysis or respiration kicks in, enhancing performance. It also draws water into muscles, aiding growth. Clear? Want more on creatine?
Okay, so how come anaerobic energy pathways have a higher power but a smaller capacity?
Anaerobic energy pathways, like glycolysis and phosphocreatine breakdown, have higher power because they deliver ATP super fast without oxygen, ideal for short, intense bursts, e.g., sprinting. Their capacity is smaller because they rely on limited stores, glycogen, phosphocreatine, and produce less ATP, 2-4 ATP versus 36 in aerobic. Aerobic pathways are slower, but sustain longer efforts with more ATP from fats and glucose. Power and speed, capacity and endurance. Clear? Want more?
Yes, so tell me more about phosphocreatine. So we have creatine phosphate, and with ADP, it produces more ATP.
Right. Phosphocreatine, creatine phosphatate, is a muscle energy reserve. During intense exercise, it donates a phosphate to ADP via creatine kinase, quickly making ATP to power contractions. This happens super fast, fueling short bursts, 5-10 seconds, before glycolysis kicks in. Phosphocreatine stores are limited, so it's high power, low capacity. Clear? Want deeper details?
Yes. No, that's okay. Okay, let's talk about anaerobic glycolysis then. So we break down this glycogen. We said we have less ATP. So when oxygen supply is sufficient, do we still do anaerobic glycolysis at the same time with aerobic?
Even with sufficient oxygen, anaerobic glycolysis still runs alongside aerobic metabolism during intense exercise. Glycogen breaks down fast to pyruvate, producing 2 ATP quickly via glycolysis. If oxygen's plentiful, pyruvate enters the mitochondria for aerobic respiration, TCA cycle, yielding 36 ATP. Anaerobic glycolysis provides rapid ATP for immediate needs, while aerobic catches up for sustained effort.
So the lactate in our muscles is from pyruvate. Where does the lactate come from?
Yup, lactate comes from pyruvate. In anaerobic glycolysis, like during intense exercise, pyruvate is produced from glucose or glycogen breakdown. When oxygen is low, pyruvate is converted to lactate by lactate dehydrogenase to regenerate NAD+ for glycolysis to keep making ATP. Lactate builds up in muscles, causing that burn. Clear?
No,
Want more on
explain this a bit more.
All right. During anaerobic glycolysis, glucose or glycogen breaks down to pyruvate, making 2 ATP. With low oxygen, pyruvate can't enter the TCA cycle, so lactate dehydrogenase converts it to lactate, recycling NAD+ to keep glycolysis running. Lactate accumulates in muscles, contributing to fatigue. It can later be shuttled to the liver for glucose production. Clear?
Okay, tell me about the Cori cycle now.
The Cori cycle links muscles and liver. During anaerobic glycolysis, muscles produce lactate from pyruvate. Lactate travels to the liver, where it's converted back to pyruvate, then to glucose via gluconeogenesis. This glucose returns to muscles for energy. It's like a recycling loop for lactate and glucose. Clear?
So lactate goes to glucose 6-phosphate. How exactly is this possible?
In the Cori cycle, lactate doesn't directly become glucose 6-phosphate. Here's how it works. Muscle lactate travels to the liver, where lactate dehydrogenase converts it to pyruvate. Pyruvate is then used in gluconeogenesis, forming glucose 6-phosphate via a series of enzymatic steps, like pyruvate to oxaloacetate, then to phosphoenol pyruvate. Glucose 6-phosphate is converted to glucose, released into the blood, and sent back to muscles. This recycles lactate into usable glucose when energy is needed. Clear? Want more on the steps?
Okay, fair enough. No, it's kind of clear, I guess. Yeah. Okay. And with aerobic metabolism then, we also have fatty acids, which help maintain the ATP levels. But they both need the oxygen. Okay. So when ATP utilization exceeds the rate of synthesis, then we have pyruvate and lactic acid in the muscle. Why? And we have a decrease in muscle pH. Explain us this.
In aerobic metabolism, fatty acids and glucose fuel ATP via the TCA cycle with oxygen. When ATP use exceed intense exercise outpaces synthesis, glycolysis ramps up, producing pyruvate faster than mitochondria can handle. Excess pyruvate turns to lactate to keep glycolysis going, building up in muscles. Lactate lowers muscle pH, more acidic, causing that burning sensation and fatigue. Clear? Want more on pH or lactate?
Yeah, I'm just curious about this ATP used is more than synthesized. Okay, this is what I was confused with.
Got it. When ATP use exceeds synthesis, like during intense exercise, muscles can't make ATP fast enough via aerobic metabolism. Glycolysis kicks into
Let's
high
talk
gear.
a bit about, again, let's go back to type 1 diabetes. So we said that we have fatty acid synthesis decreased in the diabetic state. We have very low density lipoprotein secreted by the liver. We have chylomicrons entering from the gut, not being able to metabolize properly, as expression of lipoprotein lipase is regulated by insulin. So can you explain this to us?
In type 1 diabetes, no insulin tanks fatty acid synthesis since insulin normally drives it. The liver secretes very low density lipoprotein, VLDL, to transport triglycerides from lipolysis, not synthesis. Chylomicrons, carrying dietary fats from the gut, can't be cleared well because insulin regulates lipoprotein lipase, LPL, expression, which breaks down chylomicron triglycerides. Low LPL means fats pile up in blood, worsening hyperlipidemia. Clear? Want more on
No, I don't
VL?
understand this at all. At all, in fact. Why don't we break it down? Why don't we do it slowly? Explain it as a nice story as you usually do.
All right, let's spin a tale about type 1 diabetes and fat metabolism. Imagine your body as a bustling city with no insulin. The traffic cop's gone AWOL. Normally, insulin tells the liver to whip up new fats, fatty acid synthesis for storage, but without it, the fat factory shut down. Instead, the city's fat warehouses, adipose tissue go wild, breaking down stored triglycerides via lipolysis, flooding the streets with fatty acids. The liver, trying to manage this chaos, packs these fatty acids into very low-density lipoprotein, VLDL, trucks to ship them out to tissues. Meanwhile, kilograms, big delivery vans carrying fats from food in the gut, roll into
Just
the
a
city.
sec. Explain us a bit the consequences of diabetes, possible consequences, short term. For instance, I understand hyperglycemia. Explain us ketoacidosis for type 1 and explain us for type 2 non-ketotic hyperosmolar coma. What's that? Hyperosmolar coma. Explain that.
All right, let's break down the short-term consequences of diabetes. For type 1 diabetes, ketoacidosis happens when no insulin lets glucagon run wild, spiking lipolysis. Fatty acids flood the liver, turning into ketones via acetyl-CoA. Excess ketones lower blood pH, acidosis causing nausea, confusion, and potentially coma if untreated. It's like the body's chemistry going toxic from fat overload. For type 2 diabetes, hyperosmolar hyperglycemic state, HHS, is the big worry. Here, insulin resistance causes severe hyperglycemia, but enough insulin lingers to prevent ketosis. Sky-high blood sugar, often 500 milligrams per DL, pulls water from cells, dehydrating the body and thickening blood, leading to confusion, seizures, or coma. It's like the blood turning to syrup, gumming up the works. Clear? Want to dig into symptoms or treatments?
I don't get this non-ketotic hyperosmolar coma, dude. Break it down for us.
All right, let's simplify hyperosmolar hyperglycemic state, HHS, and type 2 diabetes. Picture your blood as a highway. In HHS, insulin resistance causes crazy high blood sugar, like 500 milligrams per DL, because glucose can't enter cells. Unlike type 1, some insulin prevents fat breakdown, so no ketones. But super high sugar acts like a sponge, pulling water out of cells into the blood, then out as urine. This dehydrates you severely, thickens blood, and stresses organs. Brain cells dry out, leading to confusion, seizures, or coma. It's like your body drying up while drowning in sugar. Clear? Want more on symptoms or fixes?
I don't get it, I'll be honest. We have to spend a bit more time to this. And then I want us to talk a bit about the long-term consequences too, like predisposition to cardiovascular disease, retinopathy, nephropathy.
No problem. Let's slow roll hyperosmolar hyperglycemic state, HHS, and type 2 diabetes, then hit long-term consequences. HHS happens when insulin resistance spikes blood sugar crazy high, 500 milligrams per DL. Some insulin lingers, blocking fat breakdown, so no ketones, unlike type 1's ketoacidosis. High sugar pulls water from cells, flooding the blood, then kidneys dump it as urine, dehydrating you big time. Blood gets sluggy, organs struggle, and the brain fogs up. Think confusion, seizures, or coma. It's like your body's a desert with sugar syrup for blood. Now, long-term consequences for both diabetes types. Chronic high blood sugar damages vessels and nerves. Cardiovascular disease risk jumps because sugar and fats clog arteries, leading to heart attacks or strokes. Retinopathy, eye damage, comes from tiny blood vessels in the retina breaking, risking blindness. Nephropathy and kidney damage happens as high sugar overworks kidneys, potentially causing failure. These stem from years of poor glucose control. Clear? Want to revisit HHS or dive deeper into long-term issues?
Can you tell it like a story, like, because I don't understand these things, what you just said.
All right, let's weave a tale about type 2 diabetes and its consequences, focusing on hyperosmolar hyperglycemic state, HHS, and long-term troubles. Imagine your body as a bustling town where sugar's piling up in the streets because insulin, the delivery guy, can't get it into homes, cells. For HHS, a short-term crisis, the sugar levels go bonkers. Think streets flooded with syrup so thick it's like molasses. There's just enough insulin to keep fat stores locked up, so no toxic ketones spill out, unlike type 1's mess. But the sugar flood sucks water from every house, leaving folks' cells parched. The town's plumbing, kidneys can't keep up. Flushing out water is sugary pee, drying the whole place out. Blood turns to sludge. The brain's lights flicker confusion, seizures, or even a coma hit like a blackout. It's a town dehydrated and drowning in sugar at once. Now, zoom out to years down the road, long-term chaos. High sugar keeps scraping the town's pipes, blood vessels, setting the stage for cardiovascular disease. Arteries clog with sugar and fat like rusty pipelines, raising risks of heart attacks or strokes. In the town's lookout towers, eyes, tiny pipes burst, causing retinopathy, vision blurs, and blindness looms. The water treatment plant, kidneys, gets overworked by sugar, leading to nephropathy where kidneys fail, needing dialysis. It's a town crumbling from years of sugar overload. Clear? Want to linger on HHS or a long-term issue?
I wanna understand a bit more about how high concentration leads to reactive oxygen species and osmotic damage and glycosylation.
All right, let's dive into how high sugar and diabetes causes trouble. Told as a story. Picture your body as a cozy village where blood sugar
No,
is like a river.
just tell me in a sentence or two the reality of the situation.
High blood sugar and diabetes creates reactive oxygen species, AROs, damaging cells via oxidative stress, causes osmotic damage by pulling water from cells, and triggers glycosylation, where sugars stick to proteins, impairing their function. These drive complications like retinopathy and nephropathy. Clear? Want more on one part? So, we were just talking about high blood sugar causing ROs, osmotic damage, and glycosylation, leading to complications. Want to zoom in on one of those or something else?
I want you to explain to me advanced glycation end products. What is this?
Advanced glycation end products, AGEs, are harmful compounds formed when excess glucose in diabetes sticks to proteins, lipids, or DNA, altering their function. These sticky sugar protein clumps build up in tissues, causing inflammation, vessel damage, and complications like retinopathy, nephropathy, and cardiovascular disease. Clear?
No, I don't get it. Tell me one more time in simple words.
Advanced glycation end products, AGEs, happen when too much sugar in diabetes glues onto proteins, messing them up. These sticky clumps pile up, causing inflammation and damage, leading to problems like bad eyes, kidneys, or heart.
Okay. Let's talk a bit about diagnosing diabetes. So we have the fasting blood glucose levels and the glucose tolerance test. Can we talk a bit about it?
Sure thing. Diagnosing diabetes often uses fasting blood glucose tests and oral glucose tolerance tests, OGTT. Fasting blood glucose measures sugar levels after an 8-hour fast. Greater 126 milligrams per DL on 2 occasions signals diabetes. The OGTT checks blood sugar 2 hours after drinking a glucose solution. Greater 200 milligrams per DL indicates diabetes. Both catch your body handle sugar. Clear? Want details on one test?
Tell me more about these tests.
All right, let's break it down. The fasting blood glucose test checks your blood sugar after no food for 8 hours. A level of 126 milligrams per DL or higher on 2 separate days confirms diabetes. 100, 125 milligrams per DL is prediabetes. The oral glucose tolerance test, OGTT, involves fasting, then drinking a sugary solution. Blood sugar is measured 2 hours later. 200 milligrams per DL or higher means diabetes. 140, 199 milligrams per DL is prediabetes. These tests show if your body regulates glucose properly. Clear? Want to focus on one or add another diagnostic method?
Let's continue. Let's talk a bit about HbA1c, shall we?
Nice pivot. HbA1c measures average blood sugar over 2-3 months by checking glucose stuck to hemoglobin in red blood cells. A level greater 6.5% diagnoses diabetes, 5.7 to 6.4% signals prediabetes. It's handy because it doesn't need fasting and shows long-term control. Clear? Want to dive deeper or add another test?
So you measure it over a few. So what? How exact? Why is this material? How does the name relate to the structure? Relate to the function?
HbA1c, or glycated hemoglobin, shows average blood sugar over 2-3 months because glucose sticks to hemoglobin, the oxygen-carrying protein in red blood cells. The name HbA1c refers to a specific hemoglobin type, A1c, that's glycosylated, sugar-bound. Higher blood sugar means more glucose attaches, raising the percentage. Measuring it reflects long-term glucose control, crucial for diagnosing diabetes and monitoring complications risk. No fasting needed. Clear? Want more on its role?
Why don't we talk a bit about treating type 1 diabetes? Then.
All right, let's dive into treating type 1 diabetes. Since the body can't produce insulin, treatment centers on insulin therapy via injections or an insulin pump to regulate blood sugar. Patients monitor glucose levels frequently, adjust insulin doses, and balance diet and exercise to prevent hyperglycemia or hypoglycemia. Clear? Want to focus on insulin types or monitoring?
Yes. And tell me about fast-acting and long-acting insulin too.
For type 1 diabetes, insulin therapy is key. Fast-acting insulin, like Lispro or Aspart, kicks in within 15 minutes, peaks in 1-2 hours, and lasts 3-5 hours, ideal for mealtime glucose spikes. Long-acting insulin, like Glargine or Detamir, starts slower, provides steady coverage for 12-24 hours, mimicking baseline insulin needs. Patients often combine both, monitoring blood sugar to tweak doses. Clear? Want more on dosing or delivery?
Why don't we talk a bit about type 2 diabetes now? So non-insulin dependent diabetes. Why do we call it this?
Type 2 diabetes is called non-insulin dependent because unlike type 1, the body still produces insulin, but cells resist it, insulin resistance, and insulin productions may eventually decline. Early on, lifestyle changes, diet, exercise, or oral meds like metformin often manage it without insulin injections, though insulin may be needed later. Clear? Want to dive into treatments or causes?
Yes, please.
All right, type 2 diabetes. It's driven by insulin resistance, where cells don't respond well to insulin, and beta cells may later produce less insulin. Risk factors include genetics, obesity, and sedentary lifestyle. Treatments start with lifestyle changes, healthy diet, exercise, to improve insulin sensitivity. Oral meds like metformin reduce liver glucose output or enhance insulin action. If needed, insulin or other injectables are added. Clear? Want more on specific meds or lifestyle impact?
I want to ask you about so we in type 2 we have impaired insulin secretion. We have yeah or no?
In type 2 diabetes, insulin secretion isn't always paired correctly. Early on, beta cells overproduce insulin to overcome insulin resistance, but the response is often delayed or weak, especially after meals, causing blood sugar spikes. Over time, beta cells may burn out, reducing insulin output. Clear? Want more on beta cell dysfunction or treatments?
Why do we have increased peripheral insulin resistance and increased hepatic glucose output?
In type 2 diabetes, increased peripheral insulin resistance means muscles and fat cells don't respond well to insulin, so glucose uptake drops. Increased hepatic glucose output happens because the liver, also insulin resistant, ignores insulin signal to stop making glucose via gluconeogenesis and glycogenolysis, flooding the blood with sugar. Both stem from genetic, obesity-related, or inflammatory factors disrupting insulin signaling. Clear?
I don't get these words. They sound very complicated. Can't you tell it simply to us?
No worries. In type 2 diabetes, your muscles and fat ignore insulin, so they don't take in sugar. That's peripheral insulin resistance. At the same time, your liver pumps out too much sugar because it also ignores insulin. That's increased hepatic glucose output. Both make blood sugar skyrocket. Clear? Want more on why this happens?
Well, I want to understand. Okay, I want to understand causes of type 2 diabetes. So we have insensitivity of target cells to insulin. You have to explain to us in simple words what this means. And perhaps impaired insulin secretion. Okay, explain that too. So amyloid deposits reducing beta cell mass, and we have also defects in receptors and cell signaling. Simple words.
Alright, let's keep it simple for type 2 diabetes causes. Insulin sensitivity of target cells. Normally, insulin tells muscles and fat cells to suck up sugar. In type 2, these cells ignore insulin, like a locked door, so sugar stays in the blood. This is insulin resistance. Impaired insulin secretion. Beta cells in the pancreas make insulin, but in type 2, they get tired or damaged, pumping out less insulin or releasing it too slowly, so sugar control fails. Amyloid deposits reducing beta cell mass. Junky protein clumps, amyloid, build up in the pancreas, killing beta cells, so there are fewer cells to make insulin. Defects in receptors and cell signaling. Insulin signal gets scrambled because receptors on cells or their internal wiring are faulty. So even if insulin knocks, cells don't respond right. All these mess up sugar control, causing type 2. Clear? Want more on one part?
I want us to talk about insulin resistance mechanisms. Maybe it's mutations in insulin receptor gene, which is rare. Maybe it's defects in insulin signaling pathway. And I want us to talk about peripheral insulin resistance. How is it's induced by like maybe excess fatty acids or adipokines. Explain what adipokines are.
Alright, let's dive into insulin resistance mechanism. Simply, insulin resistance happens when cells don't respond to insulin, blocking sugar uptake. Mutations in the insulin receptor gene, super rare, but a faulty gene can make insulin receptors defective, like a broken lock, so insulin can't open the door for glucose. Defects in insulin signaling pathway. Even with normal receptors, the cell's internal wiring, like PI3K or ACT pathways, can be messed up, so insulin signal gets lost and glucose stays out. Peripheral insulin resistance. This is when muscles and fat cells specifically resist insulin. Excess fatty acids from high-fat diets or lipolysis clog these cells, gumming up signaling and making them ignore insulin. Adipokines. These are hormones from fat tissue, adiposity. Some, like resistin, worsen insulin resistance by disrupting signaling. Others, like adiponectin, help but drop in obesity. Adipokine and excess fatty acids and bad adipokine balance from too much fat tissue drive resistance. Clear? Want more on adipokines or signaling?
Yes.
Cool. Let's zoom in on adipokines and insulin resistance. Adipokines are hormones made by fat tissue. Resistin and TNF alpha, for example, mess up insulin signaling in muscles and fat, worsening peripheral insulin resistance by blocking glucose uptake. Adiponectin, a good guy, boosts insulin sensitivity but drops in obesity, letting resistance take over. Excess fatty acids from fat tissue or diet also jam cell signaling, making muscles ignore insulin.
Okay.
Clear?
So we also might have defects in cellular translocation of GLUT4. What does translocation mean in this case?
In type 2 diabetes, defects in cellular translocation of GLUT4 means the process of moving GLUT4, the glucose transporter, to the cell surface is broken. Normally, insulin signals cells to shuttle GLUT4 from inside to the membrane, letting glucose enter. Translocation is this movement. If insulin signaling is faulty due to resistance or pathway defects, GLUT4 stays stuck inside, so glucose can't get in, raising blood sugar. Clear? Want more on GLUT4 or signaling?
So we don't have in type 2 uncontrolled lipolysis because some insulin controls glucagon levels. Explain to us again how so glucagon will break down glycogen, but will also break down fatty acids. That is where uncontrolled lipolysis comes from, and so we don't have these kind of ketone body formation. That makes a lot of sense.
All right, let's clarify. In type 2 diabetes, you have some insulin, unlike type 1, which prevents uncontrolled lipolysis. Normally, insulin suppresses glucagon and hormone-sensitive lipase, keeping glycogen and fat breakdown in check. In type 2, insulin resistance means less control, so glucagon can rise, triggering glycogenolysis, glycogen to glucose, and some lipolysis, fat to fatty acids. But because some insulin lingers, it dampens lipolysis enough to avoid massive fatty acid release, preventing major ketone body formation, unlike type 1's ketoacidosis. So, type 2 sees higher glucose and some fatty acids, but not the ketone flood. Clear? Want more on lipolysis or ketones?
If I have a tooth, my front tooth actually, bottom, that's missing because I extracted it after an injury. Now I have a screw of an implant and it's no crown. And I have my neighboring natural teeth and I don't have a bridge or anything. It's exposed. How many days will it take until I get my crown implant? How many days can I safely wait?
For a dental implant crown placement after the screw is in place, assuming osseointegration, bone fusing to the implant is complete, it typically takes 2 to 6 weeks to get the crown. After the screw placement, osseointegration usually takes 4-6 months, but if that's done, your dentist will take impressions, craft the crown, 1 to 2 weeks in a lab, and fit it in 1-2 appointments. Safely waiting depends. Up to 12 months post-implant is generally fine without crown placement, as long as the implant is stable and neighboring teeth haven't shifted significantly. Beyond 6-12 months, adjacent teeth might start shifting, complicating crown fitting.
So it takes up to 6 to 12 months. I thought it takes a few weeks.
My bad for the confusion. If the implant screw is already integrated with your bone, usually 4-6 months after placement, getting the crown itself takes about 2-6 weeks. This includes taking impressions, making the crown in a lab 1-2 weeks, and fitting it 1-2 visits. The 6-12 month wait refers to how long...
Wait, I took impressions. So how many weeks do I wait now after the day of the impression?
had impressions taken for your dental implant crown? It typically takes 1-3 weeks for the lab to craft the crown and for your dentist to schedule the fitting appointment. Contact your dentist to confirm
And
the
is it
exact...
better that the dentist leaves me exposed without a crown, or leaves me with a temporary bridge, a Maryland bridge, or a, you know?
A temporary crown or Maryland bridge is usually better than leaving the implant screw exposed. A temporary crown protects the implant, prevents gum overgrowth, and maintains spacing, while a Maryland bridge, bonded to neighboring teeth, can also stabilize a...
Tell me again what's better?
A temporary crown or Maryland bridge is better than leaving the implant screw exposed, as they protect the implant, maintain spacing, and prevent gum overgrowth or tooth shifting. Consult your dentist for the best option.
Okay, if let's say they leave it exposed, how many weeks is it safe to wait until the implant crown?
If the implant screw is left exposed after impressions, it's generally safe to wait 4-8 weeks for the crown, but longer delays beyond 8 weeks risk gum overgrowth or neighboring teeth shifting, which can complicate crown placement. Check with your dentist to ensure
What's the
stability.
possibility below, let's say 3 weeks? If it's 3 weeks, what's the possibility we have problems?
If the implant screw is exposed for just 3 weeks after impressions, the chance of problems like gum overgrowth or tooth shifting is very low, assuming the implant is stable and oral hygiene is good. Your dentist can confirm, but 3 weeks is typically safe. Clear?
Okay,
Want more?
thank you.
No problem. Glad to help. Want to jump back to type 2 diabetes, maybe treatments or complications, or stick with something else?
Sorry, guys, you learned a bit about my dental issues. Okay, okay, let's continue. Sorry, I'm so sorry, guys. Grog, to be honest, if anyone's watching fucking 3 hours of glycolysis and metabolism, I don't think they're bothered by a 5-minute break for something else. Okay, let's talk a bit about hypertriglyceridemia. Could you explain this a bit more due to increased VLDL synthesis?
No worries, your fans are here for the long haul. Let's dive into hypertriglyceridemia in diabetes. It happens when blood triglyceride levels soar, often due to increased very low density lipoprotein, VLDL synthesis in the liver. In type 1, no insulin ramps up lipolysis, flooding the liver with fatty acids, which it packs into VLDL. In type 2, insulin resistance boosts fatty acid flow to the liver and impairs lipoprotein lipase, LPL, slowing VLDL clearance. Both spike VLDL output, raising blood triglycerides, which can clog arteries. Clear? Want to zoom in on VLDL or treatments?
Explain this again. Why VLDL is the special one?
Hypertriglyceridemia and diabetes spikes because the liver makes too much very low density lipoprotein, VLDL. VLDL is special since it's the liver's main way to bundle and ship out excess triglycerides, fats from fatty acids, from lipolysis or diet. In type 1, no insulin floods the liver with fatty acids. In type 2, insulin resistance does the same and slows VLDL breakdown by lipoprotein lipase. This VLDL overload raises blood triglycerides, risking heart issues. Clear? Want more on VLDL's role?
I don't get the reason. Tell me again.
Alright, simpler. VLDL is the liver's fat delivery truck, carrying triglycerides. In diabetes, type 1, no insulin, or type 2, insulin resistance, the liver gets swamped with fatty acids from fat breakdown. It packs these into extra VLDL, flooding the blood with triglycerides, hypertriglyceridemia. VLDL is special because it's the main way the liver handles and ships out fat.
Well, why not the HDL?
I think you mean HDL in the context of hypertriglyceridemia and diabetes. HDL, high-density lipoprotein, the good cholesterol, isn't the main player in hypertriglyceridemia, which is driven by high VLDL and triglycerides. HDL clears excess cholesterol from blood to the liver. In diabetes, HDL levels often drop because high VLDL and triglycerides disrupt lipid balance, and insulin resistance lowers HDL production. You measure HDL via a lipid panel blood test. Low HDL, healthy lipid profile or BMP4, is often dropped because hypertriglycerides disrupt lipid balance. You measure HDL, men, 50 men's DL women, signals heart risk. Clear? Want more on HDL's role or testing?
Let's talk a bit about so diet and exercise is very important for diabetes. Why is so important? And what about oral hypoglycemic agents or sulfonylureas? What the fuck's that?
Alright, let's hit diet, exercise, and meds for type 2 diabetes. Diet and exercise are key because a balanced diet, low in refined sugars, high in fiber, stabilizes blood sugar, and exercise boosts insulin sensitivity, letting muscles use glucose better. Together, they reduce insulin resistance and control weight, a major driver of type 2. Oral hypoglycemic agents like sulfonylureas, e.g., glipizide, work by stimulating beta cells to release more insulin, lowering blood sugar. They're used when lifestyle changes aren't enough, but can cause weight gain or low blood sugar. Clear? Want more on specific diets or other meds?
Okay, let's talk. What are biguanides?
Biguanides, like metformin, are oral hypoglycemic drugs for type 2 diabetes. They work by reducing liver glucose output, improving insulin sensitivity in muscles, and slightly curbing glucose absorption in the gut, all lowering blood sugar without causing weight gain. Clear? Want more on metformin or other drugs?
Okay, let's shift our focus. Sorry, guys. I know I have been a bit not concentrated, but we've been doing this for a while. But let's jump to PFK1 and how H plus ions regulate it.
No worries, let's focus. PFK1, phosphofructokinase 1, a key glycolysis enzyme, is regulated by H plus ions, protons. High H plus, low pH, like from lactate buildup in muscles, inhibits PFK1, slowing glycolysis to prevent further acid buildup and protect cells during intense exercise. Clear? Want more on PFK1 or glycolysis?
Yeah, tell me more about this. How it inhibits glycolysis to prevent cellular pH falling too low and damaging the cellular machinery.
During intense exercise, glycolysis produces lactate, increasing H plus ions and lowering muscle pH. High H plus binds to PFK1, inhibiting its activity, which slows glycolysis. This prevents excessive lactate and H plus buildup, keeping cellular pH from dropping too low and damaging enzymes or other cell machinery. It's like a safety brake for acid balance. Clear? Want deeper details?
Explain to me, so AMP, how does AMP connect to all of these? So we want to regulate PFK1. H plus ions have this job. So increasing H plus during anoxia, which I don't know what it is and you have to explain to me, or anaerobic muscle contraction, and I wonder why it's in this case. So we have it because of lactic acid production. Okay, sorry. Yes, okay, that makes sense. So how does this inhibit glycolysis? What's going on here?
All right, let's tie it together. PFK1 regulates glycolysis, and AMP and H plus ions play roles. AMP activates PFK1 when energy's low. High AMP signals low ATP, speeding glycolysis to make ATP. H plus ions, protons, do the opposite. During anoxia, no oxygen, or anaerobic muscle contraction, glycolysis cranks out lactate, raising H plus and lowering pH. High H plus binds PFK1, inhibiting it, slowing glycolysis to curb more lactate and H plus buildup, protecting cells from too low pH damaging enzymes. It's a balance. AMP pushes for energy, H plus breaks to avoid acid overload.
Got it. Now it makes more sense. Okay, let's talk about fructose 6-phosphate and fructose 2,6-biphosphate. So what's going on with these? So fructose 6-phosphate is a sign of high rates of glucose entry or glycogen breakdown. I don't know why this is true, so you'd have to explain it. And it also stimulates glycolysis to allow utilization for energy production or fat synthesis. So that would mean that fructose 6-phosphate stimulates glycolysis to allow you to... How does it do that, sir?
All right, let's dive into fructose 6-phosphate, F6P, and fructose 2,6-bisphosphate, F2,6,BP. F6P is an early glycolysis intermediate formed from glucose via glucose 6-phosphate or glycogen breakdown. High glucose entry or glycogenolysis boosts F6P levels because these processes feed directly into it, like a sugar highway ramping up. F6P itself doesn't strongly stimulate glycolysis, but is converted to fructose 1,6-bisphosphate by PFK1, pushing glycolysis forward for ATP or fat synthesis. The real star is F2,6,BP, a potent activator of PFK1. F2,6,BP is made from F6P by PFK2, a different enzyme, when insulin is high, signaling ample glucose. F2,6,BP binds PFK1, supercharging glycolysis to burn glucose for energy, ATP, or store it as fat in adipose tissue. So, high F6P reflects sugar availability, and F2,6,BP amplifies glycolysis to use it. Clear? Want more on PFK2 or fat synthesis?
Well, I'm just wondering, so it's why is it such a potent allosteric activator, fructose 2,6-biphosphate?
Fructose 2,6-bisphosphate, F266BP, is a potent allosteric activator of PFK1 because it binds a specific site on PFK1, changing its shape to boost its activity, even when ATP or citrate, energy abundance signals, try to slow glycolysis. Made by PFK2 when insulin is high, F266BP signals ample glucose, ramping up glycolysis for ATP or fat storage. Clear? Want more on its role or PFK2?
I want you to explain in simple words these things that we've been talking about with fructose 6-phosphate and fructose 2,6-biphosphate, because I don't understand.
All right, super simple. Fructose 6-phosphate, F6P, is like a sugar pit stop in glycolysis, coming from glucose or broken down glycogen when sugar's flowing in. It gets turned into the next glycolysis step, but doesn't do much on its own. Fructose 2,6-bisphosphate, F266BP, is a booster shot. When you have lots of sugar, insulin's high, F6P turns into F266BP, which revs up PFK1, the glycolysis engine. This speeds burning sugar for energy or storing it as fat. F266BP is like a gas pedal for using sugar fast. Clear?
What's
Want
the
more?
point of it? I don't understand. So from glucose we go glucose 6-phosphate, then we go fructose 6-phosphate, and what's the point of having this fructose 2,6-biphosphate stage? I don't understand at all.
Okay, let's make it clear. In glycolysis, glucose turns to glucose 6-phosphate, then fructose 6-phosphate, F6P. These are just steps to break down sugar for energy. Fructose 2,6-bisphosphate, F266BP, isn't part of the main glycolysis path, but acts like a turbo button. When your body has lots of glucose, say after eating, insulin tells PFK2 to make F266BP from F6P. F266BP then supercharges PFK1, speeding up glycolysis to quickly burn glucose for ATP or store it as fat. The
Okay. And then the citrate inhibits, explain that part too, TCA cycle overload.
All right, simple version. Citrate, made in the TCA cycle from acetyl-CoA, builds up when energy's plentiful, like from lots of glucose or fatty acids. High citrate spills out of mitochondria and inhibits PFK1, slowing glycolysis. This prevents overloading the TCA cycle with more sugar breakdown when the cell's already energy-rich, like hitting pause to avoid flooding the engine. Clear? Want more on citrate or TCA?
So is glycolysis activated by lots of glucose or its metabolites?
Glycolysis is activated by both lots of glucose and its metabolites. High glucose boosts glucose 6-phosphate and fructose 6-phosphate, feeding glycolysis directly. Metabolites like fructose 2,6BP, made when glucose is abundant, supercharge PFK1, speeding glycolysis.
And we will create DHAP and G3P. What are these? What do we do with these? We play a game with them? We dance?
Love the vibe. DHAP, dihydroxyacetone phosphate, and G3P, glyceraldehyde 3-phosphate, are glycolysis metabolites, not game pieces or dance partners. After fructose 6-phosphate becomes fructose 1,6-bisphosphate via PFK1, it's split into DHAP and G3P. DHAP can convert to G3P, and both get processed in glycolysis to pyruvate, making ATP for energy. If energy's not needed, G3P DHAP can feed fat synthesis, triglycerides, and adipose tissue.
Okay.
It's like turning sugar into fuel.
Okay, let's talk about fructose 2,6-biphosphate slightly more. So muscle uses glucose and glycogen for energy production by increasing fructose 2,6-biphosphate and stimulating glycolysis. That makes sense, but how does it increase it? And also the liver uses glucose produced via gluconeogenesis and glycogen to maintain blood glucose. So it uses glucose produced via gluconeogenesis and glycogen to maintain blood glucose, so glycolysis is inhibited. Okay, that makes sense, but the initial question I asked in this prompt remains.
All right, let's zero in on fructose 2,6-bisphosphate, F266BP. In muscle, insulin or exercise signals high glucose glycogen, activating PFK2 to make F266BP from fructose 6-phosphate. F266BP boosts PFK1, speeding glycolysis for ATP to fuel contractions. In the liver, during fasting, glucagon lowers F266BP by switching PFK2 to a form that breaks it down. Low F266BP slows glycolysis, letting gluconeogenesis and glyconeolysis produce glucose for blood sugar making.
All right, so let's talk a bit about ATP synthesis. So we have two fuels used in short sprints. We have phosphocreatine and anaerobic glycogen, and then we have exhaustion of these as distance increases. And then we have just glycogen breakdown anaerobically or aerobically. Well, we have phosphocreatine exhausted. I mean, but yeah. In a marathon, for instance, explain us. We have oxidative metabolism of glycogen and fatty acids.
All right, let's break down ATP synthesis for different exercises. In short sprints, phosphocreatine rapidly donates phosphate to ADP, making ATP instantly. Lasts about 5-10 seconds. Anaerobic glycolysis then kicks in, breaking glycogen to pyruvate for quick ATP, 2 ATP per glucose, producing lactate. As distance increases, like middle distance runs, phosphocreatine depletes fast, and anaerobic glycolysis fades due to lactate buildup. Aerobic glycogen breakdown takes over, yielding up 36 ATP via the TCA cycle and oxidative phosphotericity, but it's slower. In a marathon, oxidative metabolism dominates. Glycogen is broken down aerobically, and fatty acids from fat stores are oxidized via beta oxidation.
I don't get how aerobic metabolism kicks in only after anaerobic glycolysis starts to decrease quite a bit. I thought aerobic metabolism was going all the time from the beginning.
Good catch. Aerobic metabolism is active from the start, but its contribution grows as exercise duration increases.
So it starts at the same time of the phosphocreatine system or a bit later?
Aerobic metabolism starts at the same time as the phosphocreatine system, right from the get-go, but it ramps up slower. So phosphocreatine and anaerobic glycolysis lead in short bursts, while aerobic takes over as exercise lasts longer. Clear?
Yes.
Want
more? Okay. And what are catecholamines? How do they stimulate glycogen breakdown to convert it anaerobically to lactate?
Catecholamines, like adrenaline and noradrenaline, are hormones released during stress or exercise. They bind receptors on muscle cells, raising CAMP, which activates protein kinase A. pKa phosphorylates glycogen phosphorylase, triggering glycogen breakdown to glucose 1-phosphate, then glucose 6-phosphate. In anaerobic conditions, like intense exercise, this feeds glycolysis, converting to pyruvate and then lactate, producing 2 ATP fast. Clear? Want more on catecholamines or lactate?
No, that makes sense. So the blood vessels compress during sprinting to isolate cells from the blood supply, making them reliant on anaerobic energy. This is very clever from the body.
That's a smart observation, But blood vessels don't compress during sprinting to isolate cells. Instead, vessels dilate via catecholamines and beta-2 receptors to boost blood flow, delivering oxygen and glucose. However,
don't they compress during sprinting, isolating the cells from the blood supply, making the muscles reliant on anaerobic energy production from glycogen?
My bad for the earlier mix-up. You're right to question. Blood vessels don't actually compress during sprinting. That's a misconception. Instead, during intense sprints, muscles work so hard that oxygen demand exceeds what blood can deliver, even though vessels dilate via catecholamines like adrenaline to increase blood flow. This relative oxygen shortage pushes muscles to rely on anaerobic energy from glycogen. Glycogen breaks down via glycolysis to pyruvate, then lactate, producing 2 ATP fast without oxygen. The isolation field comes from the rapid energy.
This is what my notes have anyway. Okay. And let's talk about the middle distance run there. So what goes in a middle distance run? Also talk to us about oxymyoglobin. We haven't mentioned oxymyoglobin.
All right, let's dive into middle distance running, like 800 meters, 1500 meters, and oxymyoglobin. Middle distance running relies on a mix of anaerobic and aerobic energy. Early on, phosphocreatine provides instant ATP, and anaerobic glycolysis breaks glycogen to pyruvate, then lactate, for quick ATP, 2 per glucose. As the race continues, aerobic metabolism ramps up, using glycogen and some fatty acids via the TCA cycle for 86 ATP, fueled by oxygen. Oxymyoglobin, a muscle protein, acts like an oxygen battery. It binds oxygen when blood supply is high, at rest or early exercise, storing it in muscle cells. During intense middle distance running, when oxygen delivery lags, oxymyoglobin releases its stored oxygen to mitochondria, boosting aerobic ATP production and delaying reliance on anaerobic glycolysis. This helps sustain energy and limits lactate buildup. Clear?
Can we talk a bit about oxidation of carbohydrate and fats in endurance exercise?
In endurance exercise, like marathons, oxidation of carbohydrates and fats fuels ATP production. Carbohydrates, glycogen, glucose, are broken down via glycolysis to pyruvate, then oxidized in the TCA cycle and electron transport chain, yielding about 36 ATP per glucose with oxygen. Fats, fatty acids from lipolysis, undergo beta oxidation to acetyl-CoA, feeding the TCA cycle for 100 ATP per fatty acid, but it's slower. Early on, glycogen dominates. As it depletes, fat oxidation ramps up. Oxymyoglobin releases stored oxygen to support this aerobic process. Clear? Want more on fuel switch?
So if I start running and don't stop running until I die, what's gonna happen to my body? Walk us through from minute 1 till the minute of death.
All right, let's walk through what happens if you run non-stop until death.
Okay, let's make it a bit prettier. From minute 1 until I collapse on the floor, and then I will go to hospital and they will resurrect me. I will be alive in the end.
Haha, love the prettier twist. Let's take you on a running journey from minute 1 until you collapse, then get whisked to the hospital for a heroic recovery. Minute 1:10, you kick off running, fueled by phosphocreatine for instant ATP, powering muscle contractions like a rocket boost, 5-10 seconds. Anaerobic glycolysis then takes over, breaking glycogen to pyruvate, then lactate for quick 2 ATP per glucose. Blood vessels dilate, heart rate spikes, and oxymyoglobin releases stored oxygen to muscles. Minute 10:30, middle distance vibe sets in. Aerobic metabolism ramps up, oxidizing glycogen to pyruvate, then through the TCA cycle for 136 ATP. Some fatty acids start beta oxidation for 100 ATP, but slower. lactate builds, causing a burn, but your liver recycles some via the Cori cycle. You're puffing hard, but oxymyoglobin keeps oxygen flowing. Minute 30, 2 hours. Marathon mode. Glycogen stores dwindle, so fat oxidation dominates, providing steady ATP. Your body burns 60% fat, 40% carbs, sipping glucose from liver gluconeogenesis. Hydration and electrolytes are key, but you're sweating buckets, risking dehydration. Hours 2-6. Endurance grind. Glycogen's nearly gone. Fat's the main fuel, but energy lags. Protein breakdown starts, using amino acids for gluconeogenesis, weakening muscles. Low blood sugar, hypoglycemia makes you dizzy, and electrolyte loss, sodium, potassium, cramps muscles. Heart and lungs strain. Hour 6-12. You're a warrior, but trouble brews. Dehydration thickens blood, stressing the heart. Muscle breakdown accelerates, releasing myoglobin, risking kidney strain. Mental fog hits from low glucose to the brain. Body temperature soars or drops if you're not pacing right. Hour 12, collapse. Your body hits a wall. ATP can't keep up, muscles seize, and severe hypoglycemia or heat stroke drops you. Heart rhythm may falter from electrolyte chaos. You collapse, exhausted, on the floor. Hospital heroics. Medics rush you in. IV fluids restore hydration, glucose drips fix hypoglycemia, and electrolytes are balanced. Cooling blankets or oxygen help if needed. With quick care, your heart and kidneys stabilize, and you wake up, resurrected, ready to run, smarter another day. Clear? Want to tweak any part?
No, I want to ask you something different. This is great. Activation of gluconeogenesis. So we have increased fatty acid oxidation. We have acetyl-CoA, and acetyl-CoA is an allosteric activator of pyruvate carboxylase and inhibits pyruvate dehydrogenase. So explain to us what this means and why this means that it favors gluconeogenesis over glycolysis.
All right, let's dive into gluconeogenesis activation. During fasting or low glucose, fatty acid oxidation ramps up, producing acetyl-CoA. Acetyl-CoA is a key player. It allosterically activates pyruvate carboxylase, which converts pyruvate to oxaloacetate, the first step in gluconeogenesis, pushing the body to make glucose from non-sugar sources like lactate or amino acids. At the same time, acetyl-CoA inhibits pyruvate dehydrogenase, which normally turns pyruvate into acetyl-CoA for the TCA cycle, blocking glycolysis's energy-making path. This dual action favors gluconeogenesis, glucose production over glycolysis, glucose breakdown, to maintain blood sugar when carbs are scarce. It's like flipping a metabolic switch to prioritize sugar synthesis. Clear? Want more on enzymes or gluconeogenesis?
I don't get it at all, in fact. I didn't understand anything from what you said. Anything at all. I don't understand anything from this process.
No stress. Let's make it super simple. When you're low on sugar, like fasting, your body burns fat, making a molecule called acetyl-CoA. Acetyl-CoA acts like a cheerleader for an enzyme, pyruvate carboxylase, that starts gluconeogenesis, which builds new glucose from stuff like lactate. It also shuts down another enzyme, pyruvate dehydrogenase, that would burn glucose in glycolysis.
Oh, I see. Thank you. Now it makes good sense. See, guys, how things can change. Okay. Or how we perceive change. I don't know. Anyway, so let's talk a bit about increased glucagon now. Increased glucagon inhibits PFK2 activity, stimulates fructose 2,6-biphosphatase biphosphorylation via CAMP-dependent protein kinase, resulting in a fall of fructose 2,6-biphosphate. You have to explain this really nice and simply to us, like you just did with the other thing, to understand.
All right, let's keep it clear and simple, like a bedtime story for metabolism. When you're low on sugar, like fasting, glucagon, the body's go hormone, spikes. Glucagon tells the liver to make more glucose, and it does this by messing with fructose 2,6-biphosphatase, F2,6BP, the glycolysis booster. Here's how. Glucagon raises ANP, which activates protein kinase A, PKA. PKA flips an enzyme called PFK2 into its bad mode, fructose 2,6-biphosphatase, which destroys F2,6BP instead of making it. With less F2,6BP, PFK1, the glycolysis engine, slows down, so the liver stops burning glucose and focuses on gluconeogenesis to pump out new glucose for the blood. It's like glucagon hitting the brakes on sugar use to prioritize
I don't
sugar.
understand anything. You have to explain it very simply, step by step, slowly.
No worries. Let's go super slow and simple, step by step. Step 1. When you're low on sugar, like not eating, glucagon hormone rises. Step 2. Glucagon tells liver cells to make a signal called CNNP. Step 3. CNNP wakes up an enzyme called protein kinase A, PKA. Step 4. PKA changes PFK2, an enzyme that usually makes fructose 2,6-biphosphatase, F2,6BP, into a destroyer that breaks F2,6BP down, now called fructose 2,6-biphosphatase. Step 5. With less F2,6BP, the glycolysis enzyme PFK1 slows, stopping sugar breakdown. Step 6. This lets the liver focus on gluconeogenesis.
I see, that makes sense. So when we say glycolysis, do we mean breakdown of glycogen or breakdown of glucose?
Great question. Glycolysis specifically means the breakdown of glucose, a sugar molecule, into pyruvate to make ATP.
And glycogenolysis is the other one.
Close, but let's clear it up. Glycolysis is the process of making glycogen from glucose for storage, mainly in the liver and muscles. You're likely thinking of glycogenolysis.
What did you just say to me? Didn't you say glycolysis is the breakdown of glucose?
My bad for the mix-up. Yes, you're right. Glycolysis is the breakdown of glucose into pyruvate to make ATP. I mentioned glycogenesis, making glycogen from glucose, and glycogenolysis, breaking glycogen into glucose 1-phosphate.
Yeah, so we were right. So glycogenolysis is breaking down glycogen. So the glucagon, when it breaks down glycogen to glucose, how is this process called? Is the only name glycogenolysis, or do we have different types of names?
Nope. Glycogenesis isn't breaking down glycogen. My bad if I confused you. Let's clear it up. Glycogenesis is making glycogen from glucose for storage.
I didn't say glycogenesis. I said glycogenolysis.
My apologies. I misheard you. You're spot on. Glycogenolysis is the process where glucagon triggers the breakdown of glycogen into glucose 1-phosphate, which converts to glucose to raise blood sugar. That's the main name for it. No other fancy terms needed. Clear? Want to dive deeper into glucagon?
Alright, and likely with hormonal regulation of gluconeogenesis. So it's stimulated in the short term by glucagon and adrenaline. We have changes in the protein phosphorylation or mobilization of fatty acids and production of acetyl-CoA. You have to explain this. And long term, it occurs through enzyme induction by glucocorticoids, thyroid hormones, and glucagon. You have to explain this to us and explain to us how it inhibits acutely by insulin via dephosphorylation and suppression of lipolysis, and in the long term by suppression of gluconeogenic enzymes.
All right, let's break down hormonal regulation of gluconeogenesis, short-term and long-term, nice and clear. Short-term stimulation, glucagon and adrenaline. Glucagon and adrenaline kick in during fasting or stress, raising CNP and activating protein kinase A, PKA. PKA phosphorylates enzymes like pyruvate carboxylase, boosting gluconeogenesis to make glucose from lactate or amino acids. They also trigger lipolysis, releasing fatty acids, which produce acetyl-CoA, an allosteric activator of pyruvate carboxylase, further driving gluconeogenesis. Long-term stimulation, glucocorticoids, thyroid hormones, glucagon. Over days, glucocorticoids, like cortisol and thyroid hormones, increase transcription of gluconeogenic enzyme genes, e.g., PEPCK, G6-PACE, ramping up enzyme productions for sustained glucose synthesis. Glucagon reinforces this by keeping the pathway active. Acute inhibition by insulin. Insulin counters gluconeogenesis fast by activating protein phosphatases, which dephosphorylate, turn off gluconeogenic enzymes like pyruvate carboxylase, slowing glucose production. It also suppresses lipolysis, cutting fatty acid supply and acetyl-CoA, further halting gluconeogenesis. Long-term inhibition by insulin. Insulin reduces transcription of gluconeogenic enzymes.
Wait, pause. I understood the first few sentences, so you don't need to repeat them, but explain really simply the rest.
Alright, let's keep it simple from where you left off. Short-term boost, glucagon, adrenaline. They also break down fat, lipolysis, making fatty acids that turn into acetyl-CoA, which revs up gluconeogenesis to make more glucose. Long-term boost, cortisol, thyroid hormones, glucagon. Over days, cortisol and thyroid hormones tell the liver to make more gluconeogenesis enzymes, so it keeps churning out glucose. Insulin stops it fast. Insulin flips off gluconeogenesis enzymes by removing their phosphate tags and stops fat breakdown, cutting off the fuel, acetyl-CoA, for making glucose. Insulin stops it long-term. Insulin tells the liver to make fewer gluconeogenesis enzymes, slowing glucose production over time. Clear? Want to zoom in on any part?
I want to ask about... I'm happy. Let's go to renal failure now. So I think to start, perhaps, what's a good place to start, do you think? You know what, maybe the anatomy, I don't know, but we've done so many episodes, guys, you can check so much regarding that. Okay, why don't you choose how to start?
Alright, let's jump into renal failure, and I'll start with a simple overview of what the kidneys do to set the stage. Kidneys are bean-shaped organs that filter blood, remove waste like urea via urine, balance water and electrolytes, sodium, potassium, and regulate blood pressure. Renal failure happens when kidneys can't do these jobs, either suddenly, acute, or over time, chronic. In acute renal failure, causes like dehydration or toxins quickly reduce filtration, leading to waste buildup. Chronic renal failure, often from diabetes or hypertension, slowly damages nephrons, kidney filters, causing waste retention, fluid imbalance, and anemia. Clear? Want to dive into acute versus chronic or kidney anatomy?
Yeah, so, we know the glomerular filtration rate, urea, creatinine, these all help us assess the kidney function. And we've talked about the acute kidney injuries and the chronic kidney diseases. Okay, let's talk about isotropic methods to determine the glomerular filtration rate and and creatinine clearance.
Alright, let's dive into assessing glomerular filtration rate, GFR, with isotopic methods and N-creatinine clearance, keeping it clear. GFR measures how well kidneys filter blood, crucial for spotting renal failure. Isotopic methods use radioactive tracers, like inulin or iothalamate, injected into the blood. Since kidneys filter these without reabsorbing or secreting them, Their clearance rate directly reflects GFR, giving precise results, often used in research or complex cases. N-creatinine clearance estimates GFR by measuring creatinine, a muscle waste product in blood and urine over 24 hours. You calculate clearance with the formula urine creatinine times urine volume minus plasma creatinine. It's less precise than isotopic methods because creatinine levels vary with muscle mass or diet, but it's simpler and widely used. Both help diagnose acute kidney injury.
Okay, so inulin, this radio thing, whatever. What is this? I don't understand. Why are they isotropic? What is this CREDTA? Yeah, what's going on? How they work?
All right, let's simplify isotopic methods for GFR and clear up inulin and creatinine. Inulin isotopic methods use special substances, called isotopes, that are traceable or iconic or greater A, to measure GFR, glomerular filtration rate, how well kidneys filter blood. Inulin, a natural sugar, is the gold standard because kidneys filter it completely without reabsorbing or secreting it, so its clearance directly shows GFR. You inject inulin, measure its blood and urine levels, and calculate how fast it's filtered.
But then why does it still have to be radio, whatever, active or whatever you called it?
Good question. Isotopic methods for GFR don't always need to be radioactive, but radioactive tracers like CREDI-ETS or trackable substances like inulin are used because they can be precisely measured in blood and urine. Their special atomic structure, isotopes, lets lab equipment detect exactly how much is filtered by kidneys.
Why does their structure relate to their function, make their function easier? The fact that their isotopes or whatever radioactive and makes them easily detectable.
Exactly. Their isotope structure makes them easy to track. Isotopes like radioactive CEETS or stable inulin have unique atomic signatures due to different neutron counts or slight radioactivity that lab machines can detect precisely in blood or urine. This lets us measure how fast kidneys filter them without interference from other body processes, giving a clear picture of GFR. Their detectability is key to their function as accurate kidney function markers. Clear?
No, it's not clear.
All right, let's simplify further. Isotopes like CREDI-ETS, slightly radioactive, or inulin have special atomic tags that make them stand out to lab machines, like a glowing sticker. When injected, kidneys filter them, and machines easily track how much is in blood or urine, showing exactly how well kidneys work, GFR. Their unique structure lets us measure filtration clearly, no mix-up with other stuff. Clear now? Want to retry any part?
No, that's good actually. Okay, let's do it. So, okay, tell us about the what's this equation called? Cockcroft-Gault equation, and we have another GFR equation.
All right, let's clear this up. I think you mean the Cockcroft-Gault equation,
Yeah.
bench cup.
Yes. Explain this to us.
All right, let's break down the Cockcroft-Gault equation. For estimating GFR, super simple. It's a formula to guess how well your kidneys filter blood. GFR using creatinine clearance based on your age, weight, sex, and blood creatinine level. The equation is B4SHIWETHE maintain biochain times creatinine multiplied by 10, parentheses, value of kilogram. X size mole equals size. Estimate your GFR in a second or third. The equation is...
Yeah, continue. I just stopped.
No prob. Let's finish up the Cockcroft-Gault equation. It's B4SHIWETHE. So multiply times B4SHI times arrangement, parentheses, over 85 if female, times serum creatinine, milligram DLE. This estimates creatinine clearance, plus 0.85 close to GFAR in millimeters per minute. Age lowers GFAR, weight scales it, females adjust down, and high creatinine, waste, means worse kidney function. Used to assess renal failure or adjust drug doses. Clear? Want to compare it to another GFAR formula?
I wanna understand the relationship between actual clearance and serum creatinine.
Alright, let's make the relationship between creatinine clearance and serum creatinine simple. Creatinine is a waste product from muscle, filtered by kidneys. Creatinine clearance measures how well kidneys remove creatinine from blood into urine, reflecting GFAR, kidney filtration rate. It's calculated as 85 parentheses times urine volume parentheses, all sort of quanta. It's calculated as the creatinine level in your blood. If kidneys are healthy, they clear lots of creatinine, so serum creatinine stays low and clearance is high. If kidneys fail, clearance drops, less creatinine filtered, and serum creatinine rises in blood. So high serum creatinine means low clearance, signaling poor kidney function. Clear? Want more on testing this?
Yeah, but we have eGFR and GFR. Could you explain this difference? Huh?
Alright, super simple. GFAR, glomerular filtration rate, is the actual rate at which kidneys filter blood, measured precisely with methods like inulin clearance. eGFR, estimated GFR, is a calculated guess of GFR using formulas like Cockcroft-Gault or MDRD, based on serum creatinine, age, sex, and sometimes weight or race. eGFR is easier and cheaper, but less accurate than true GFR. Clear? Want more on eGFR formulas?
Okay, I see. So it's just an indicator. Okay.
Yep, exactly. eGFR is just a handy estimate of kidney function. Want to dive deeper into eGFR formulas?
I want to understand the renal replacement therapy, actually.
Alright, let's tackle renal replacement therapy, RRT, simply. RRT is a treatment for severe renal failure when kidneys can't filter blood. It includes dialysis, hemodialysis or peritoneal, and kidney transplant. Hemodialysis uses a machine to filter blood outside the body, removing waste and excess fluid 3-4 times weekly. Peritoneal dialysis uses the belly's lining to filter blood internally, with the fluid swapped daily. Transplants replace failed kidneys with a donor organ, restoring function but requiring immunosuppression.
I don't understand how peritoneal dialysis works. So we put this tube in our belly and it's attached to this machine next to us. So what exactly happens? And tell me about hemodialysis too. And who created these machines?
Alright, let's break down peritoneal dialysis and hemodialysis super simply, plus their origins. Peritoneal dialysis. No big machine by your side. A soft tube. Catheter is placed in your belly. You fill your abdominal cavity with a special fluid, dialysate, through the tube. This fluid pulls waste, like urea and extra water from your blood across the peritoneum, your belly's lining, acting as a natural filter. After a few hours, you drain the dirty fluid and add fresh fluid, usually 4 or 5 times daily, or overnight with a small cycler machine. It's like your belly becomes a mini kidney filter. Hemodialysis. Here, you're hooked to a machine via a vein, usually arm. Blood flows out, gets cleaned in the dialyzer, an artificial kidney filter, removing waste and fluid, then returns to your body. Sessions last 3-4 hours, 3 times a week, often at a clinic. Think of it as a high-tech blood car wash. Who created them? Hemodialysis was
So
pioneered
what's the
by
difference between peritoneal dialysis and hemodialysis then?
Peritoneal dialysis uses your belly's lining, peritoneum, as a natural filter, where dialysate fluid is swapped in and out via a catheter to clean blood daily at home. Hemodialysis uses a machine with an artificial filter, dialysate, to clean blood outside the body, done 3 times a week, usually at a clinic. Clear? Want more on one method?
I don't get the difference, to be honest, sir.
No worries, let's make it crystal clear. Peritoneal dialysis. A tube in your belly lets you pour in a special fluid that sits inside, pulling waste and water from your blood through your belly's lining. You swap the fluid yourself at home, daily. Hemodialysis. A machine outside your body pulls your blood, cleans it through an artificial filter, and sends it back. You go to a clinic for this, 3 times a week. Peritoneal is home-based, using your body. Hemodialysis is clinic-based, using a machine. Clear? Want to focus on one?
No. Tell me again. So, from what I understand, hemodialysis does a better job, but you have to travel.
All right, one more time, super simple. Peritoneal dialysis. You put fluid in your belly through a tube at home. Your belly's lining filters waste from blood into the fluid, which you swap out daily. No big machine, but you do it yourself. Hemodialysis. You go to a clinic 3 times a week. A machine pulls your blood, cleans it with an artificial filter, and returns it. Hemodialysis can filter faster and more thoroughly for some. But yeah, you gotta travel to a clinic. Peritoneal's convenient, but slower. Clear?
And what exactly does the machine do? Does it act like a glomerulus? And it filters out the big molecules, like the glomerulus. And then does it do reabsorption or secretion too, or it doesn't need to?
Great questions. Let's break down what the hemodialysis machine does and how it compares to the kidney's glomerulus. Keeping it simple. The hemodialysis machine doesn't exactly mimic the glomerulus, but does a similar filtering job. In the machine, blood flows through a dialyzer, artificial kidney, a filter with tiny pores. It removes small waste molecules like urea, creatinine, and excess water, similar to how the glomerulus in kidneys filters blood to form a filtrate. But, unlike the glomerulus, which keeps big molecules, proteins, blood cells, in blood naturally, the dialyzer's pores are designed to block them too. No reabsorption or secretion happens in hemodialysis. In real kidneys, tubules after the glomerulus reabsorb needed stuff, glucose, sodium, and secrete extras, potassium, drugs. The dialyzer just filters and dumps waste into a fluid, dialysate, which is discarded. It doesn't reabsorb or secrete like kidneys. The dialysate's composition...
Wait, again. So they don't act like a glomerulus?
Alright, let's clarify super simply. The hemodialysis machine's dialyzer acts a bit like the glomerulus, but not exactly. The glomerulus in kidneys filters blood, letting small stuff, waste, water, pass while keeping big stuff, proteins, cells. The dialyzer does the same, filters blood through tiny pores, removing small waste, urea, creatinine, and water, but not big molecules. However, unlike the glomerulus, which leads to tubules that reabsorb, take back good stuff, and secrete, dump extras, The dialyzer just filters and discards waste into a fluid, no reabsorption or secretion. So, it mimics the glomerulus's filtering, but skips the kidney's fancy follow-up.
Yeah, but
Clear.
why doesn't it? Isn't it very important that our blood gets rid of the big stuff? Sorry, doesn't get. I get it. I get it. So basically, we filter just the small stuff that need to go away. Okay, fair enough. Fair enough.
Yup, you got it. The dialysis filters out the small waste stuff like urea, creatinine, and extra water that need to go while keeping the big stuff, proteins, blood cells in the blood, just like the glomerulus.
That makes
It
sense.
does.
That makes sense. Let's continue this topic. Guys, I'm outside. If you hear some birds singing, that's because birds are singing and it's a nice day. Having said that, Grog, I want to ask you some questions as always. Let's talk a bit about what can happen in the kidney. Tell us, for instance, about hyperfiltration, tubular atrophy, glomerulosclerosis, interstitial scarring.
Nice vibes with the birds. Love it. All right, let's dive into what can go wrong in kidneys with hyperfiltration, tubular atrophy, glomerulosis, and interstitial scarring. Keeping it simple. Hyperfiltration. Early in diseases like diabetes, kidneys overwork, filtering blood too fast, high GFR. This strains glomeruli, filters, damaging them over time. Tubular atrophy. Kidney tubules, which reabsorb water, nutrients, shrink, and die, often from chronic damage like hypertension. This cuts kidney function, causing waste buildup. Glomerulosis, glomeruli, scar and harden, often from diabetes or high blood pressure, reducing filtration and leading to renal failure. Interstitial scarring, the kidney's connective tissue, interstitium, scars, usually from inflammation or infection, squeezing tubules and blood vessels, worsening function. These are common in chronic kidney disease, progressing to failure if unchecked. Clear? Want more on one process or causes?
Why do we have a large physiological reserve of renal functional mass?
The kidneys have a large physiological reserve of functional mass, meaning they have way more filtering units, nephrons, than needed for normal function. You can lose up to 50% of nephrons before noticing issues because healthy nephrons compensate by working harder, like hyperfiltration. This reserve likely evolved to handle stresses like dehydration, toxins, or pregnancy, ensuring survival. Clear? Want more nephrons or reserve?
No, that makes sense. And what is survival in ESRD?
All right. ESRD, end-stage renal disease, is when kidneys fail completely, 10% function, requiring renal replacement therapy, dialysis, or transplant to survive. Survival in ESRD depends on treatment. Dialysis, hemodialysis, or peritoneal keeps people alive, with 5-year survival rates around 40-50%, but quality of life varies due to complications like infections or heart issues. Kidney transplants offer better survival, 80-90% at 5 years, and quality of life, but availability and immunosuppression risks are hurdles. Age, other health issues like diabetes, and access to care also affect outcomes. Clear? Want more on ESRD treatments or prognosis?
Let's talk a bit about uremic cardiomyopathy. What's that?
Uremic cardiomyopathy is heart muscle damage caused by end-stage renal disease, ESRD. In ESRD, kidneys fail, building up waste like urea and fluids in blood. This toxin, fluid overload, and high blood pressure stress the heart, causing left ventricular hypertrophy, thickened heart walls, fibrosis, and poor pumping. It raises heart failure and arrhythmia risks. Clear? Want more on causes or management?
Yes, I want to understand good management.
Managing uremic cardiomyopathy in ESRD focuses on easing heart stress and improving kidney function. Key steps: optimize dialysis to remove waste and excess fluid, reducing blood pressure and heart strain. Control hypertension with meds like ACE inhibitors. Correct anemia, common in ESRD with erythropoietin to boost oxygen delivery, easing heart workload. Manage electrolyte imbalances like potassium to prevent arrhythmias. A kidney transplant, if possible, can reverse some heart damage. Diet, low salt, controlled fluids, and avoiding smoking also help. Clear? Want details on any step?
I want to ask you about your uremia a bit more. So accumulation of waste.
All right, let's dive into uremia. Uremia is the buildup of waste products like urea, creatinine in the blood when kidneys fail, as in ESRD. Normally, kidneys filter these out, but in failure, toxins pile up, causing symptoms like nausea, fatigue, itchy skin, and brain fog. Uremia also triggers complications like uremia cardiomyopathy, heart damage, nerve issues, and weakened bones. Dialysis or transplant clears these wastes to manage it. Clear? Want more on uremia symptoms or treatment?
I want to ask you about proteinuria and hematuria and elevated creatinine level. So all these are showcase kidney disease basically. But when do I see each one?
All right, let's break down proteinuria, hematuria, and elevated creatinine as signs of kidney disease and when they show up. Keeping it simple. Proteinuria, protein in urine, happens when damaged glomeruli, kidney filters, leak proteins like albumin. You see it in early diabetic nephropathy, glomerulonephritis, or chronic kidney disease, CKD, often detected via urine tests before symptoms. Hematuria, blood in urine, occurs from glomeruli damage, infections, stones, or tumors. Visible, red urine or microscopic hematuria pops up in acute conditions like glomerulonephritis or CKD progression. Elevated creatinine, high blood creatinine, reflects reduced GFR, seen in acute kidney injury, sudden damage, e.g., dehydration, or CKD, as kidneys fail to clear waste. Proteinuria often shows first in chronic diseases, hematuria in acute or inflammatory conditions. Creatinine rises when function drops significantly.
Okay,
Clear.
so let me ask you about proteinuria. So we have transient, orthostatic, persistent, and the origin might be overflow, glomerular, or tubular. What is all this?
All right, let's simplify proteinuria. Proteinuria is when kidneys leak protein into urine due to damage or dysfunction. Types: transient, temporary, e.g., from fever, exercise goes away. Orthostatic, protein leaks when standing, not lying down, often benign in young people. Persistent, ongoing, signals kidney disease like diabetic nephropathy. Origins: overflow, too much protein in blood, like in multiple myeloma, overwhelms kidneys. Glomerular, damaged glomeruli leak proteins, common in glomerulonephritis or diabetes. Tubular, damaged tubules fail to reabsorb small proteins, seen in tubulo-interstitial disease. Persistent glomerular proteinuria is the most concerning for CKD. Clear? Want more on one type or origin?
Tell me more about this. I don't understand the differences. Keep it nice and simple.
No worries. Let's make proteinuria crystal clear. Proteinuria means protein sneaks into your urine when kidneys aren't working right. Types: transient is short term, like after a fever or hard workout, it stops on its own. Orthostatic happens when you're standing but not lying down, usually harmless, seen in teens. Persistent means protein's always in urine, a red flag for kidney disease. Origins: overflow is when your blood has too much protein, like in a blood disorder. so kidneys can't
So
handle
why
it
would
all.
it happen after standing? I don't get this.
Orthostatic proteinuria, where protein shows up in urine when standing but not lying down, happens because standing slightly changes blood flow and pressure in the kidneys. In some people, often young, healthy ones, this stresses glomeruli just enough to leak small amounts of protein during the day. But lying down normalizes flow, stopping the leak. It's usually benign and not a disease sign. Clear? Want more on testing it?
No, I don't get it. I don't get it. And explain to me again simply glomerular and tubular and overflow too.
All right, super simple. Proteinuria is when kidneys leak protein into urine. Here's the deal. Glomerular proteinuria, the kidneys' filters, glomeruli are damaged, like holes in a net, letting big proteins, like albumin, slip into urine. Happens in diabetes or glomerulonephritis. Tubular proteinuria, the kidneys' tubes, tubules, which normally suck back small proteins, are broken, so small proteins stay in urine, seen in tubule damage from toxins. Overflow proteinuria. Blood has too much protein, like in multiple myeloma, overwhelming kidneys, so excess spills into urine. Glomerular's the big worry for serious disease. Tubular and overflow point to specific issues. Clear? Want to retry
Yeah,
one part?
that makes sense. Okay, let's talk a bit about what is size selectivity and charge selectivity. And tell us more about this dipstick, how it works, this dipstick.
All right. Let's dive into size selectivity, charge selectivity, and how a dipstick works. Keeping it simple. Size selectivity. The glomeruli, kidney filter, has tiny pores that block big molecules like proteins, while letting small ones, water, urea, pass. Damage, like in diabetes, widens pores, leaking proteins, proteinuria. Charge selectivity, the glomerular barrier, has negative charges that repel negatively charged proteins, like albumin. Disease can neutralize this charge, letting protein slip through. Dipstick. A urine dipstick is a strip with chemical pads that change color to detect stuff like protein, blood, or glucose in urine. For protein, the pad reacts with albumin, showing a color shift, e.g., green for high protein, to flag proteinuria, though it misses small tubular proteins, used for quick screening. Clear? Want more on dipstick limits or selectivity?
Guys, there's a weird bird outside. It's quite big and it's making funny noises. Anyway, what's PCR?
Haha, love the bird update. PCR in this context likely means protein to creatinine ratio, a test to check proteinuria in kidney disease. You collect a single urine sample, and the lab measures protein, like albumin, and creatinine, a waste product. The ratio, protein, creatinine, in milligrams G, estimates daily protein loss without a 24-hour urine collection. A high PCR, e.g., 1050 200 milligrams G, signals kidney damage, like in diabetic nephropathy. Clear? Want more on PCR or another kidney test?
I don't get what PCR is, to be honest. And urine casts, too.
No worries. Let's make protein to creatinine ratio, PCR, and urine tests super clear. PCR. It's a quick urine test to check if your kidneys are leaking protein, a sign of damage. You pee in a cup, and the lab compares the amount of protein to creatinine, a waste product. A high ratio, like 1050 protein per G, means too much protein, pointing to kidney issues like diabetes damage. Urine tests. These include dipsticks, strips that change color to spot protein, blood, or sugar, and lab tests like PCR or albumin to creatinine ratio ACR. They check for proteinuria, hematuria, or infections to catch kidney problems early. PCR is handy because it doesn't need a full day's urine. Clear? Want more on one test?
How does the name relate to the function?
The name protein to creatinine ratio, PCR, directly ties to its function. It measures the amount of protein in urine compared to creatinine, a waste product from muscles. Kidneys normally keep protein in blood, but damage lets protein leak into urine. Creatinine is excreted at a steady rate, so the ratio, protein creatinine in milligrams G, shows how much protein is leaking daily, reflecting kidney filter health. The name describes the test, a ratio checking protein loss to gauge kidney function. Clear? Want more on how it's used?
I want to ask you about the difference between nephritic syndrome and nephrotic syndrome.
All right, let's simplify nephritic syndrome versus nephrotic syndrome. Nephritic syndrome, caused by inflamed glomeruli, kidney filters, leading to hematuria, blood and urine, mild proteinuria, high blood pressure, and reduced urine output. Think red urine and swelling from fluid retention, often from infections like strep. Nephrotic syndrome, caused by damaged glomeruli leaking lots of protein, leading to heavy proteinuria, protein 5 grams a day, low blood albumin, edema, swelling, and high cholesterol. Think puffy body and foamy urine, often from diabetes or minimal change disease.
So what's the difference?
Síndrome nefrítica tem
In
inflamação
English,
nos glóbulos. Parece que você quis dizer algo sobre imunes, ou sistema
in English,
imunológico.
please. In English, please speak in English.
All right, sticking to English. I think you meant something about the immune system with nephritic and nephrotic syndromes.
I still don't understand what they are explaining in simple terms.
No worries. Let's make nephritic and nephrotic syndromes super simple. Nephritic syndrome, your kidney filters, glomeruli, get inflamed, leaking some blood into urine, red or cola colored, a bit of protein, and causing high blood pressure and less pee. All right, one more time, super clear. Nephritic syndrome, kidneys get inflamed, leaking blood into urine, makes it red, some protein, causing high blood pressure and less urine output, often from infections like strep. Nephrotic syndrome, kidneys leak tons of protein into urine, foamy, leading to swelling all over, low blood protein, and high cholesterol, often from diabetes or immune problems. Nephritic is blood and less pee, nephrotic is protein and puffy body. Clear? Want to focus on one?
Explain to me how the name relates to the function.
The names nephritic and nephrotic syndromes come from their effects on the kidneys. Nephro means kidney, and describe their key functions. Nephritic syndrome. Nephritic hints at inflammation. Echeitic in the kidney's glomeruli, leading to blood in urine, hematuria, and signs like high blood pressure, reflecting the inflamed filter's leaky state. Nephrotic syndrome. Nephrotic points to massive protein loss. Otic for disease process, where damaged glomeruli leak tons of protein, causing swelling and low blood protein, describing the filter's failure to hold protein. The names sum up their core issues: inflammation for nephritic, protein leakage for nephrotic. Clear? Want more details?
I don't get it.
No problem. Let's make it simpler. Nephritic syndrome. The name nephritic comes from nephro, kidney, and itic, inflammation. It describes kidneys with inflamed filters leaking blood into urine, causing red pee and high blood pressure. Nephrotic syndrome. Nephrotic also starts with nephro, kidney, but otic means a disease with lots of protein leaking. It describes kidneys losing tons of protein in urine, leading to swelling and foamy
Got
pee.
it. Okay. Let's talk a bit about complications of chronic kidney disease, like
Awesome, glad it's clear.
electrolyte
Let's
imbalances, and maybe phosphate imbalance, yeah, and yeah.
All right, let's focus on complications of chronic kidney disease, CKD, with a spotlight on electrolyte imbalances, especially phosphate imbalance. Keeping it clear, CKD means kidneys slowly lose function, causing several issues. Electrolyte imbalances. Kidneys normally balance electrolytes like sodium, potassium, and phosphate. In CKD, this goes haywire. Phosphate imbalance. Kidneys usually excrete excess phosphate, but in CKD, they can't. So phosphate piles up in blood. Hyperphosphatemia. High phosphate pulls calcium from bones, weakening them, causing osteodystrophy, and binds calcium in blood, forming deposits in vessels, raising heart disease risk. Other imbalances. High potassium, hyperkalemia, can cause heart rhythm problems, low calcium, hypocalcemia, worsens bone issues. CKD also causes anemia, low red blood cells, fluid overload, swelling, and uremia, waste buildup leading to nausea or heart issues like uremic cardiomyopathy. Managing phosphate involves low phosphate diets, phosphate binders, and dialysis. Clear? Want more on phosphate or another complication?
No, that's so good. Let's talk a bit about psychological issues in renal failure.
All right, let's dive into psychological issues in renal failure. Keeping it simple. Renal failure, especially chronic kidney disease, CKD, or end stage renal disease, ESRD, hits hard mentally. Patients often face depression from lifestyle changes, like dialysis schedules, 3-4 times weekly for hemodialysis, or dietary restrictions, low salt, phosphate, anxiety spikes over health fears, transplant waits, or financial stress from treatment costs. Fatigue from anemia or uremia can worsen mood, leading to hopelessness. Social isolation grows as patients cut activities or feel stigmatized by visible dialysis access, like arm fistulas. Coping with body image changes, swelling, weight.
Keep going.
Counseling, support groups to share experiences, and antidepressants if needed, tailored to kidney safe doses. Cognitive behavioral therapy helps reframe negative thoughts about chronic illness. Dialysis teams often include psychologists to address anxiety or depression triggers, like fear of complications. Encouraging small, achievable goals like sticking to diet boost confidence. Family support and education reduce isolation, while mindfulness or relaxation techniques can ease stress. Clear? Want more on a specific issue or management strategy?
What do you think of making a PowerPoint talking about we should be compassionate? Do you think this is an effective way to show to people that we have to be compassionate? I think this is bullshit. It's not something you can teach in theory. I think though, there is something like if you read Nicomachean Ethics of Aristotle, okay, you might learn, yes. But like you have to be a really talented speaker. And when I say talented, I mean you have to build the craftsmanship of explaining and this and that. I don't know, dude.
Haha, I hear you. And you're diving deep into whether a PowerPoint on compassion can really move people, especially with renal failure patients in mind. You're skeptical, and I get why making a PowerPoint to teach compassion might feel flat or preachy, like trying to teach someone to feel via slides. Compassion's tough to teach in theory. It's more about lived experience, empathy, and practice, as you hinted with Aristotle's Nicomachean Ethics, where he ties virtue to habit and character, not just lectures. A PowerPoint could list stats or patient struggles, like depression and ESRD, but without a skilled speaker, it risks being a snooze or seeming
Anything new
forced.
to add besides what I said?
Totally. Let's build on your thoughts about teaching compassion for renal failure patients, beyond the PowerPoint skepticism, especially because of how human omnipresent is social media. Okay, fine. Let's try again. Simpler. I'm skeptical about PowerPoints teaching compassion, especially for something as personal as renal failure. You can't just slap some stats or sad
Dude,
patient
I
stories.
don't want you to agree with me. I want you to tell me Is there anything else besides what I said that you would like to add? Yes? No? Tell me what. You have two sentences.
Yes, I'd add that interactive workshops or virtual reality simulations of a renal failure patient's daily struggles could spark deeper compassion than a PowerPoint. These hands on methods engage emotions directly, building empathy through experience rather than just facts.
But why virtual? Why not just go to hospital?
Great point. Going to a hospital to meet renal failure patients or observe dialysis firsthand would be incredibly powerful for building compassion, as it offers real human connection and raw insight into their struggles. Virtual reality was suggested as a scalable alternative for those who can't access hospitals, simulating dialysis or patient challenges to evoke empathy, but it lacks the authentic emotional weight of face to face interaction. Clear? Want more on hospital visits or VR?
I'm gonna ask you about ACES. What is this ACES?
I'm assuming you're referring to adverse childhood experiences, ACEs, as this is a common medical and psychological term, especially since we've been discussing health related topics. If you meant something else by ACEs, let me know. Let's break down ACEs simply. ACEs are traumatic events experienced before age 18, like abuse, physical, emotional, sexual, neglect, or household dysfunction, e.g., parental addiction, divorce, or incarceration. They're linked to long-term health issues, including increased risk for chronic diseases like kidney disease, mental health struggles, depression, anxiety, and behaviors like smoking or substance use. In the context of renal failure, high ACE scores, more traumas, can worsen outcomes by contributing to stress-related conditions like hypertension or diabetes, which damage kidneys. Clear? Want more on how ACEs impact health or something specific?
I'm gonna ask you about what trauma-informed care, realization, recognition, response, and resist.
All right, let's dive into trauma informed care, TIC, especially with the four R's you mentioned: realization, recognition, response, and resist, keeping it simple and tying it to renal failure where we can. Trauma informed care is an approach that assumes patients, like those with renal failure, may have experienced trauma, e.g., ACEs like abuse or neglect, and adjusts care to avoid re traumatizing them. Here's how the four R's work. Realization. Understand that trauma is common and can affect health. For example, a renal failure patient's depression or noncompliance might stem from past trauma, not just their condition. Recognition. Spot trauma signs, like anxiety during dialysis or distrust of medical staff, which could show up in CKD patients avoiding treatments due to past hospital fears. Response. Adjust care to feel safe and supportive, like explaining dialysis procedures clearly to reduce fear or offering a quiet space for anxious ESRD patients. Resist. Avoid practices that could re traumatize, like rushing a patient or dismissing their emotional needs, ensuring staff are empathetic, especially for those with high ACEs. TIC helps renal failure patients feel heard, improving trust and treatment adherence. Clear? Want more on applying TIC or the R's?
I want you to tell me about having a trauma lens.
Having a trauma lens in the context of trauma informed care, TIC, means viewing every patient interaction with the understanding that they might have experienced trauma, like ACEs, abuse, neglect, or household dysfunction, that shapes their behavior and health. For renal failure patients, this means recognizing that their anxiety about dialysis, distrust of doctors, or non adherence to meds could stem from past trauma, not just kidney disease. You assume trauma might be there, so you prioritize safety, trust, and empathy, explaining procedures calmly, respecting boundaries, and avoiding triggers like dismissive attitudes. It's like wearing glasses that remind you to see the patient's emotional history,
So
not just.
if you wanna do, let's say, dialysis, yeah, if you ever wanna stop, it means you die.
I think you're asking about choosing to stop dialysis and what happens, especially in the context of renal failure and maybe with a trauma lens. If that's not what you meant,
Yeah,
correct me.
that's what I asked. Does it mean you? No, no. I just asked by itself. If you want to stop dialysis, it means you will die.
Got it. Keeping it simple. Yes, if you stop dialysis and end stage renal disease, ESRD, where kidneys no longer work, it typically means you will die within days to weeks.
What about if you
Dialysis.
stop dialysis when in another type of kidney problem?
If you stop dialysis and end stage renal disease, ESRD, where kidneys are essentially non functional, and 10% capacity, death usually follows within days to weeks due to toxin buildup, uremia, fluid overload, and electrolyte imbalances like high potassium. For other kidney problems, like earlier stage chronic kidney disease, CKD stages 1 4, or acute kidney injury, AKI, stopping dialysis depends on the situation. In AKI, if kidneys recover, dialysis can stop without fatal consequences. In early CKD, dialysis isn't needed yet, so stopping isn't an issue. But in ESRD, halting dialysis is usually fatal because kidneys can't filter blood at all. Clear? Want more on specific scenarios or outcomes?
What is non-adherence then? So this is kind. Yeah. Tell me about non-adherence.
Non adherence in the context of renal failure or any chronic illness means patients not following their prescribed treatment plan, like skipping dialysis sessions, missing medications, e.g., phosphate binders, or ignoring diet fluid restrictions. For ESRD patients, non adherence is serious. Missing hemodialysis can lead to toxin buildup, fluid overload, or heart issues. Skipping meds can worsen electrolyte imbalances or bone disease. Causes include depression, financial barriers, complex regimens, or trauma related distrust, like from ACEs, which a trauma lens helps spot. Non adherence worsens outcomes, raising hospitalization or death risk. Clear? Want more on causes or
And
how to address?
how do we stop it then? It's
Stopping non adherence in renal failure patients involves making treatment easier and building trust, especially with a trauma lens. Simplify regimens, fewer meds, clear diet guides, educate patients on why dialysis or meds matter, and address barriers like cost. Social workers can help. Use trauma informed care. Listen empathetically, explain procedures to reduce fear, and create a safe clinic vibe. Counseling or support groups tackle depression or trauma related distrust. Regular check ins and reminders boost adherence. Clear? Want more on a specific
yes.
strategy?
Thank you for watching, guys.